Hello everyone and welcome to the Machine Learning with Python course. Today, machine learning is behind so many things we use every day, from product recommendations and fraud detection to price prediction, chatbots, medical diagnosis, and even self-driving technology. But machine learning is not magic. At its core, it's about teaching computers to learn patterns from the data and make predictions or decisions. And that is exactly what we'll learn in this course. We'll start by understanding what machine learning really means and how it is different from AI and deep learning. Then we'll explore the main types of ML, especially supervised learning, where models learn from the data that already has known answers. Next, we'll move into regression, where you'll learn how machine learning models predict continuous values like house prices, sales, revenue, or customer spending. We'll also build our first linear regression model using Python and scikit-learn. You will learn how to split data into features and labels, divide it into training and testing sets, train the model, and make predictions. After that, we'll understand how to check if our model is performing well using evaluation metrics like mean squared error, RMSE, and R-square. Then we'll look into common problems like overfitting and underfitting and learn how techniques like ridge and lasso regression help improve model performance. We'll also cover important preprocessing steps like scaling, one-hot encoding, pipelines, and column transformer, so your machine learning workflow becomes cleaner and more practical. Once regression is clear, we'll move into classification, where the goal is to predict categories like spam or not, fraud or not fraud, disease or no disease. You will learn classification models like logistic regression, KNN, decision trees, and support vector machines. We'll also understand important classification metrics like accuracy, precision, recall, F1 score, confusion matrix, ROC curve, and AUC. Finally, we'll touch on advanced classification concepts like multi-class classification, multi-label classification, imbalanced data sets, oversampling, undersampling, and ensemble models. By the end of this course, you will understand how machine learning models are built, trained, tested, evaluated, and improved using Python. So let's get started and learn how machines actually learn from data. Also, if you're interested in mastering the future of technology, the professional certificate course in Gen AI and Machine Learning is the perfect opportunity for you. Offered in collaboration with the ENICT Academy IIT Kanpur, this 11-month live and interactive program provides hands-on expertise in cutting-edge areas like Gen AI, machine learning, and tools such as ChatGPT and Hugging Face. You will gain practical experience through 15+ projects, integrated labs, and live masterclasses delivered by esteemed IIT Kanpur faculty. Alongside earning a prestigious certificate from IIT Kanpur, you will receive official Microsoft badges for Azure AI courses and career support through Simplilearn's Job Assist program. Hurry and enroll now. Find the course link in the description box and pin comments. So let me ask you a quick question before we start. Which ML type learns from the data with correct answers? A. Supervised learning, B. Unsupervised learning, C. Deep learning, and D. Reinforcement learning. Let me know your answers in the comments below.
These are available and almost like self content available. So nothing much into this. This is just theory part. We'll quickly wrap up with that theory section first, and then we'll move on to the more important part. That is the conceptual things. So in the first presentation, that is machine learning, the first part, we're going to talk about the course introduction. Essentially, we're going to talk about what is in store for you. So what are we going to cover up? What are the topics? We'll talk about those things. So that's your learning part. Here it goes. We'll talk about what is machine learning. That will be the first lesson, introduction to machine learning, all theory into that. Different kind of machine learning. What are the types of machine learning? What are the different categories of this? Where is what is used? What I will cover up in this course, what is beyond the scope of this course, everything I'll cover up into that first particular presentation. From after this, we will move on to the supervised learning techniques, and we'll start with the regression algorithms. We'll understand what is regression, why regression, what is the algorithms that we use in regression, what is the mathematics behind them, how do we apply them, where do we apply them, right? Everything will be covered up. We'll cover up more models into that. We will try to cover up the variants of regressions. We'll also cover up some optimization techniques into that, where we try to optimize the models. We'll understand regularization techniques. So there will be a detailed discussion onto that too as well. As soon as we reach onto that topic, I'll give you a detailed agenda that this is what we're going to cover up into this course. But just an overview, this is what we're going to cover up in regression course. Then we will have supervised learning algorithms of classification. 4 or 5 algorithms, the basic algorithms. We'll start with them and then move on to the advanced algorithms, or we'll move on to the ensembling techniques as well in this course at the later stage. But we'll look into different types of classification problems, multi-class, multi-label, and the variants, right? So we'll look into all kinds of variants, all kinds of examples, which is possible into this kind of scenario, because in real world terms, you would see that we will have majority of the problems that we solve are classification. Majority, I'll say it's a ratio of 85-15 between classification and regression if we talk about supervised learning. So yes, regression, we will talk about a lot of algorithms. Classification, we'll talk about algorithms. There are certain algorithms which are common to both regression and classification. So we'll cover those algorithms while dealing with the classification part. Moving on, we will have ensembling techniques. That's a great way to combine or join together multiple types of models. How do we join them? There are multiple approaches to that. We'll discuss all those, right? Enhancing the performance of my models. Then we'll move on to the different leg of classification of the machine learning algorithm, which we call as unsupervised algorithms. So in which we will learn about majorly three categories. We learn about the clustering techniques. We learn about the dimensionality reductions. We look into the anomaly detection as well, right? We will look into the imbalanced class classification as well, imbalanced class problems. So a lot of things will come up under the unsupervised learning algorithms. Then we'll finally move on to the last topic, which is recommendation systems. Therein, we will take up a Netflix dataset and we'll try to see how Netflix works on the movie recommendations. So that's what the real world example. We will have different techniques, how recommendation system works. There is, user-based filtering or content-based filtering or algorithm-based filtering like support vectors, not support vector, but singular vector machines. Right. So we'll look into that. Everything will be coming into the picture. Essentially, that would be the all topics. We have 6 lessons to cover up, and I will count it as 12 days only. 13th day, I like to devote onto the project work. So we will spend a little less time on complete theory part, some basic theory things. Concepts and practice is the maximum time that I'll devote into, right? There is one simple request that I would like to have. Now, essentially, I can tell that I know approximately 7 to 8 programming languages, including Python. Coding is my blood. I love it. Course component wise, a few things like you have hands-on exercises, which I'll do with along with you. Course and project we'll discuss on the last day. Ebooks or the presentations that are available into your learning management portal. You can download it from there. So any PPTs that will show up on the screen, they are available as PDF documents on your. And in case you're not seeing the reference material, get in touch with the LSM. She will arrange the things for you. Good, great, Mary. Okay, so we have presentation number 2. That's essentially the last presentation that I have. Beyond this, I don't have any presentations to show up because this is the last theory thing. After beyond this, I have only concepts to deliver. There is not too much of concepts into this, so we'll talk about this now. And we'll start with the point that what is machine learning? Some people are aware what is machine learning, so I can expect some responses onto that. What is machine learning? Or those who are not aware can give me a generic idea. Whatever they think, what is your opinion about what is machine learning? You might see me looking on the right side. So there I have a chat window. I am looking onto that so that I can read the responses quickly. So team, be aware that I will try to respond as quickly as possible because I am doing the live chat monitoring on the right side of my screen. I have another machine. Anybody, what is machine learning? People from IT background? Training models, Kishore, generic words, learn from the data, Chetan, great. Computer learn the data, good, Mary. MI is a branch of ML is a branch of AI. Yep, machine that learns from exposed data. Good, Manjunath. Ability to learn patterns from numerous data from human behavior. Getting into the behavioral science. Great, Suleiman. Good. None of the responses are bad. All are good. So great. But let me just break it down to a very small or very conceptual level. What exactly we are trying to achieve, right? What is the purpose or what is the basic role that machine learning does? Learn from the data and improve performance automatically. Agreed. Sangamesh. Now, let me just bring it up for you. Now, let's imagine that a very simple problem. Idea behind is problem solving. We need to solve certain problems. The entire concept or entire purpose behind the entire industry, I will say that, is to solve problems. Whatever the nature of problem is, how, but we're trying to solve a problem. So I'm bringing into a picture a very simple problem for you, right? The problem is that I want to add two numbers. Is it simple adding two numbers? Very simple thing, right? Now what happens is, what we have is a machine, right? We have a machine, let's say a computer, right? What you will do to this machine, I will give the inputs, input A, suppose, and input B. There are two numbers, I have given those inputs. Now what is going to happen? I need to write down a piece of code. I have to write down a piece of code that will add A and B together, and this machine will process this code and give me the output. Do we agree on that? That's the traditional approach of programming. Now into this, let me ask this. Who writes this code? The code is written by people like you and me, right? The coders, software developers, engineers, whatever you want to say them, SDEs, whichever profile you want to take. But that code is written by people like you and me. Acceptable? Now, in order to write these codes, we require some skills. There are certain skill sets that's required. You should know the programming language, you should know the data structures, you should know the algorithms and everything. Does that make sense? In order to effectively write that code. It says that instead of doing this to the machine, I will direct a certain pieces of algorithms. So these algorithms are pre-written mathematical concepts, right? These algorithms are basic concepts of mathematics or statistics or somewhere else, right? Some neural concepts as well are there. But these algorithms I'll supply to this machine, right? And to this machine, along with the inputs, I will also tell what my output is, what my expected output is. Now, while solving a problem in traditional approach, we know what are the inputs, we know what are my expected outputs. What we look is a pathway to reach from input to the output. Correct? Now, here again, I know what my inputs are. I know what is my expected outputs are. Test cases, right? If there is any software tester in the house. Good. So we'll supply those to machine and let the machine decide to find out the relation between input and the output. How can it reach from input to the outputs? And what it is going to generate is a piece of code. The machine is going to generate a piece of code. We generally call that as a model. What we get is a model out of it. Good. It has solved my problem. It has given me a potential solution by which when I give the inputs A and B, I am expecting it to give me an output. It will give me an output. This output I will say as my prediction. Now, how good or bad is that output? I can compare this output from what my original output was. Right? Now, in this scenario, what is the role of a human? Just like people like you and me. What's our role? Do I need to make logical coding for the model? No. So do I need to know about data structures and algorithms? Typically, no, you do not have to. What you need to know about is what sort of algorithms, because these are, let's say, there's thousands of algorithms available, right? Out of those algorithms, which algorithm is applicable to solve this problem? So I need to make, or I need to just tell it that, okay, in the pool of 10, choose this one. So what we have to do is the selection process. Make sense? And come out to a conclusion that out of the all algorithms, which one is doing the best job? Are we good? Great. So machine learning, now if I have to give you a contextual definition or theoretical definition, machine learning is a branch of artificial intelligence, right? So if you talk about AI, AI is a bigger picture. AI is a big picture. Into that AI, we have a subsection called as ML. That ML has another subsection, we call it as DL or deep learning. And DL has another subsection, we call it as FN, foundational model. Great. So what we're looking into is right now, AI is a very vast field because AI also involves robotics. It also involves some neural networks. A lot of things are there into AI. So AI is a very big term. Within AI, machine learning is a sub part of it. So what we are learning in this course is only the machine learning concepts. We are not going into the AI part. We are not going into the DL part. We are not going to the FM part. Those are subsequent things that will follow up in the later in the course. So it's a branch of AI, right? Typically, that's what I can say about machine learning, which learns or which understands the data or pattern, right? About the data, right? It learns from the data, it gets understanding from the data, and tries to give me a solution to a problem. It gives me solution to a problem, and it learns by experience. The more amount of data, the more exposure to the information that it gets better and better, right? So what I'm trying to make is an intelligent computer. Now, if you talk about the word machine learning, it was I think so. Arthur Samuel was the person, if I don't remember rightly. Arthur Samuel. He quoted this term somewhere around 1950s. I exactly don't remember the year, but somewhere in 1950s he quoted this term. So, so ML, if we talk about machine learning, is not a new concept. It's a concept that was there way back in history, right? Early 1950s or maybe somewhere around 1960s. ML was there. The only thing was it was not applicable or it was not being used practically because of its cost. Machine learning was, was a very cost-consuming activity. And if you go back in time, you will see that the cost of machine, cost of data management, cost of processing instructions was very, very high. These days, it has become cheaper. Cost of storage is cheaper now. Cost of processing instruction is cheaper. And machines these days are quite advanced as compared to the machines that we had earlier. So that's the only reason why we have seen a upsurge in the field of AI, because the computational cost has decreased a lot and it's keep on decreasing right now, right? I am expecting all of you are AI enthusiasts, machine learning enthusiasts, so you should be aware about, or you should have been following the recent developments in the field of AI. Can you tell me, anybody tell me, which is the most recent thing that was in news about artificial intelligence? Anybody? Anthropic? Yes, Chetan. Anthropic what? OpenClaw, chatbots, Cloud AI. Yep, Cloud AI, what version? OpenClaw, OpenClaw. It was Opus 4.6, if I'm not wrong. Opus 4.6. It has created a lot of things, many things juggled up around the world. Nonetheless, so team, we also need to look into the perspective that learning the coding part is not as important. Then more important part is why we are doing that. Always try to focus on why we are doing it, right? Not what we are doing, because these days we have certain very good AI tools like Opus 4.6. We have, I've not tested it yet. We have GitHub Copilot. We have Microsoft's Copilot version as well. We can use Gemini. Right. So there are a lot of AI tools which generates the code for you based upon a simple prompt. So I will not try to bother a little bit too much about the coding part. I will do live coding with you. I'll tell you what each line of code means for you, so that you understand why we are doing action, what action or what it completes up for us. We'll do that. But the point is, if the coding part is not getting through to you, no problem, but understand the concept more. Is that okay? In the field of machine learning, why is more important than what? Moving on. Okay. So we'll have some start. Okay. So AI, it's a subset of AI that assists the systems to learn and improve automatically from experience without being explicitly programmed. So we're not programming a machine, we're just letting it know. Good. Arthur Samuel, 1959. So correct my year. Okay. This is a quick difference between a traditional approach. We have discussed that, and machine learning approach. I would like you guys to give that a quick read. So that's about machine learning, artificial intelligence. So artificial intelligence is a bigger picture. Within that, we have a subset called as ML. ML's subset is deep learning. Deep learning subset is foundational models. FM. Foundational models, right? So I will not say that foundational models. Many people do not talk about foundational model explicitly, but for example, there are certain models like let's say BERT. If someone has heard about BERT, or llamas. All these are very basic foundational models which are developed on basis of some research papers. So these are foundational models that stands as my base models when I try to create a certain different kind of models in the field of AI. So yes, these are typically based upon deep learning concepts, a subset of deep learning, but a separate branch of dealing with the core models which are trained up. Let's say, for example, ChatGPT. ChatGPT in itself is a model, right? So that model has been trained upon a humongous amount of data. I cannot train it up on my machine, but I can still use its feature to create my own ChatGPT or kind of thing. Right? So that is what we call it as the foundational models. So basic models that are there. So AI generic example, self-drive car, machine learning, Amazon Alexa is an example, but I would not say that is an example, Amazon Alexa, because Alexa has improved over the period of time. Alexa now understands natural languages as well and can process and take up AI decisions as well. So yeah, decision making process has improved in Alexa. So Alexa cannot be considered just a machine learning example. In machine learning, we are only doing the prediction, giving a generic idea, right? It's Alexa will fall into the category of deep learning now, lesser than, right? Then we come to the deep learning example. Anything which is expected that only human can achieve or done by a machine is deep learning, right? Anything that expected is only human. Like say, for example, I write my hand. Can I write down something on my handwriting? Okay, I change the color of a picture. Right? A painter can do it. A human can do it. How can a machine do it? Right? So that's what. For example, you need to edit your photograph and make yourself a little bit more, brighter and sharper. You can do it through a software, but you require a human intervention. Can I do it without human intervention? The answer is yes. How? Deep learning algorithm. You say a word in Chinese and it can be translated into any language automatically. right? You see the notes coming up right in front of the screen, whichever language you choose. Let's say I'm speaking English, someone wants to understand the things in Hebrew. You have choices available to read my text or read the transcripts in Hebrew as well. These are things which are available through deep learning concepts. Good. Great. Now, let's get some into the history of machine learning, history of AI. Right? Use of AI. Typical example which is given to you on the screen is about a chess. A chess, when a machine or a computer and a person plays up a chess, the computer uses the moves by the human in order to understand and learn more and decide its future actions. Right? Can someone tell me the name of the machine which defeated? So it was a simple machine, a very simple machine at that point of time, as compared to the standards that we follow today, right? That was able to defeat Gary Kasparov. He was the grandmaster and world champion at that point of time. Second one was Vishwanathan Anand from India, who later on became the world champion. That's a separate thing. The 8 by 8 square board in chess. In Go, we have 64 by 16 by 16, if I'm not wrong. So, lot of space is there. It's a more complex game as compared to chess. A machine was able to defeat that too, was able to win the Go game as well. The name of the machine that won that game was AlphaGo. In some year. So idea still remains the same. I am going to create machines that can perform certain tasks. Problems can solve my problems, right? But in order to solve the problems, I am not going to tell it how to solve the problems. It will learn on its own how to solve that particular problem. It is going to learn on its own. The only thing that I'll tell to the machine is what processes or what steps you should follow. Are we good? That will be the basic idea that we'll try to do with the machine learning part. Good. Where is machine learning used? Almost everywhere. You think of anything, we have machine learning there. In current day scenario, anything that you think of connected to electronics, machine learning is always there. Anything these days. Spam filtering, your emails get filtered, your resumes get filtered up because of machine learning. When I do a social media analysis, right, any kind of analysis on social media, what is in trend, what is not in trend, machine learning, any kind of customer service chatbots, these are deep learning concepts. Online recommendation systems, again deep learning concepts and some part of ML. Sentiment analysis, you will rate me at the end of session, right? I will look into your comments and find out how is the sentiment of the session, and I'll try to alter my leaving out too many digital footprints, and everything is being utilized by the world in order to generate certain data. You can check the use of machine learning, a very basic understanding of leaving digital footprint. You take up any Google search or meta search and search for anything. Let's say I search for a comb, right? Then start playing a third party game anywhere. You will see ads of that comb only. Anybody experience that? You search on a different site about something, and later on you start seeing the ads on the same thing on your machine. Or another example I'll tell you, where recommendation system works. Giving you a small little example of recommendation system. Many of you would be fond of watching shorts, maybe also on video streaming platforms. You might see some small little shorts like people like Instagram, people like YouTube, or anything of those formats. Have you ever observed that if you try to spend a little time on certain types of shots, later on you will see the similar kind of shots coming up in your scrolling list? It's not that they do not have other shots, but you will see the one that you prefer to watch out, you gave little more than 2 seconds, did not scroll back to the next for within 1 second or 2 seconds. Usually it's a 2 second timeline. If one person spends more than 2 seconds on a particular video, that is considered as area of interest. Usually 2 seconds time. Every organization have their own standards, but usually 2 seconds. So I'm talking about a very basic understanding that what machine learning can achieve for us. Are we good? Great. Now we'll have some basic understanding of what is machine learning, what are the different types of machine learning, where it is being used, right? So as I told you, in machine learning, we have a pool of algorithms. So what are these pool of algorithms? These are predefined rules, predefined structures, which a machine can use to establish the relation or solve a problem. I use the word solve the problem because not every time I want to establish a relationship, but there is some kind of relationship activity that will happen either in supervised, unsupervised, or reinforcement or semi-supervised. Wherever you go, all four categories of machine learning, we will have some kind of relationship that is being established by the machine, right? And for this, we have algorithms. And my objective in this course is to teach you those algorithms. How those algorithms work, what is the basic understanding of those algorithms, how does they help in making decisions, right? What we are going to use algorithms for, we're going to use predict the outcomes, classify the targets, improve the performance of the models. So a lot of things will happen. Very important aspect. This is very, very important, very, very critical for us. While doing the machine learning thing, while we are working with the machine learning problems, what is most important is two things: the quality of the data and the quantity of the data. I cannot have a very small data and still solve a problem. I cannot have a huge data, but that's not. This small little chart talks about the importance of quality data and quantity data, right? So, so more quantity, performance, but at some point of time, uh, at some quantity, this will become flattened, right? And this is also going to flatten out at a later stage. So after a certain point of time, there is no increase. Essentially, not in machine learning, but if we talk about the deep learning algorithm, the moment quantity increases, it goes in exponential way like this. So deep learning models are essentially better than machine learning models, but in some small certain problems, machine learning models are more effective as compared to deep learning. So both things are important. And secondly, why we need to learn machine learning when deep learning is more into the word is very simple reason. Without going through machine learning, it's not possible to get into the deep learning because you will not understand how deep learning works without understanding the concepts of machine learning. Maybe in real world scenario, as on date, most of the things that are used in real world is deep learning concepts. Machine learning is kind of getting obsolete over the period of time. Machine learning is not practically used. However, in order to build your understanding about deep learning, it's very, very important, critical to get to know about the machine learning first. Good. Okay. Let's talk about types of machine learning. Anybody aware what are different types of machine learning that we have? I've taken those 4 names right away, 10 seconds ago, maybe 10 minutes ago. So as a part of machine learning, we have 4 categories. There are 4 types of machine learning. We have supervised, we have unsupervised, then we have reinforcement, and we have semi-supervised. So these are 4 categories of machine learning, out of which we are only talking about the 2 in this course is supervised and unsupervised. We will not be dealing with the reinforcement learning. We are partially dealing with the semi-supervised. Reinforcement learning in itself is a different topic. It is something which comes in and goes out. If you talk about the market of reinforcement learning, I'll show up a video to you about reinforcement learning, right, in a short while from now. So these are the 4 categories or in which the machine learning is divided: supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. Let's have an example. In supervised learning, what happens is we will have a data, right? In that data, I will have some features. That means I will have columns that I'll use to predict an outcome. I will have a target, right? So I'm going to make learning based upon inputs and outputs. I will supply my inputs, I will supply my outputs. The machine is going to learn from both inputs and outputs and generate a model. And this model will be tested out for us. Good. So that's a typical example that you can see here. I'm sorry. So in supervised learning, what we will have is a labeled data. Let me give you a real world example of labeled. What is the use of labeled data? Anyone who uses Meta, these days called as Meta, earlier it was called as Facebook. If you go back in history, you might remember, some of you might, that at some point of time in history, it used to ask whenever some persons ask or uploads a picture, it tells that tag the person in the pictures. Then you need to put up a person's a square onto that person's face and write it down the name. Anybody seen that before in the past? Meta? Hopefully someone would have. Nowadays, if you upload a picture, it does an auto tagging. It gives you suggestions whether you want to tag it up. That's a separate thing, right? So at the time when it was asking you to tag the people, what it was doing is it was collecting data to train its model to do the tagging or to identify, or creating the labels, because creating labels for data is not an easy job. You need a lot of time, you need a lot of things, right? For example, if I talk about one of the very famous competition, ISLRVC, we call it as, that contains approximately, I don't remember, I guess 25 million images are there into that. And models are trained on those 25 million images. Those 25 million images were randomly captured and are labeled manually in order to create the labels. So a labeled data, that means I'm telling that what does a particular input, for a particular input, what is the output. So that is its label, right? Or the target will. So if I have a target to predict, I will say that as a labeled data, and I will use that using the supervised machine learning algorithms. If I have to predict the target, are we good? Now, think about a data where I do not have a target to predict. I have certain data which contains only the inputs. No output is available to me. Possible, right? In this scenario, what we do is we do a grouping, right? We do a grouping of the data. I'll use the word grouping. Either I will try to see what rows are together which are of similar type, if any groups can be made out, 2 groups, 5 groups, 10 groups, whatever the number of groups. Or maybe if there are columns which can be grouped together to create something. So column wise grouping, row wise grouping, right? When you do a column wise grouping, we call that as dimensionality reduction. When you do it for the row wise, we call it as clustering, right? These are the two approaches, and we call this process of grouping the data where I do not have the target, but we look into similarities or differences in the data to find out what we can manage together, right? That is what we call as unsupervised learning. I do not have the labels. That is why no supervision. Okay, I did not talk names. I'll talk about those names. Right. This slide talks about some supervised machine learning algorithms. Linear regression we are covering. Decision trees we are covering. Logistic regression we are covering. SVM we are covering. All 4 algorithms. There are more algorithms apart from this which I'll cover up in the upcoming time. Let's get into the unsupervised learning, right? So unlabeled data, that's the keyword here. We have unlabeled data, and if I have to segment the images, find out different things in an image object, group, user group based on commonalities, anomalies over geographical landscapes. So essentially, unlabeled data means where I do not have a target. Very in basic layman terms, I can say that. We look into these kind of data problems as well. What is the purpose? This is a typical example where I can showcase the unsupervised learning. I have a group of people. I do not know who's what. There's a herd of people coming up, or mass people. I will try to interpret some logic, and it has divided the people into different categories. 1, 2, 3. They have all have some similarities between them. This is a group of females. This could be, I don't know. This is male. This looks like teens. This look like kids. This look like old people. This may be families. Could be anything or whatever. Young women, young people. Grouping can be anything. Good. It could have been any category classification. I'm not bothered. But the point is, as per my decision making process, whatever the similarity or commonality that I was looking into the groups, I am able to create labels. What will be the advantage? I will be able to create labels onto this. Suppose this is my feature. I have certain things. I have categorized that, okay, this belongs to category 1. So I can create a category 1 feature over there. And I can later on use this labeled data to apply supervised classification algorithms to help it out or solve problems. So if I have unlabeled data, I can use unlabeled or unsupervised machine learning algorithms to label the data. I can use that. That may not look very convincing, but yes. Then we have semi-supervised learning, right? Now in semi-supervised, what we have is a combination of supervised learning and unsupervised learning. The part is that I have a small labeled data, and we have a large unlabeled data, right? So what I'll do here is, in a very simple algorithm, first of all, I will use the small data. Let me show it with example. I have a small data which is given some labels, right? So I have data about adults and I know about the kids. So what I will do is, first of all, based upon these labels, divide my unlabeled data into that labeling, right? So I will have people falling in the adult category. I will have people falling in the kids category. right? So first division, so that is supervised division done. That after doing that supervised division, I will further divide it based upon the similarity and dissimilarities within those classifications, within those divisions, right? So supervised followed by unsupervised approach. That is where we call it as semi-supervised. So there is small little bit of data that is available to identify, but bigger chunk is not identifiable. There is grouping is being done. So here I can have babies, teens, and tweens. I have senior citizens, youths, and adults. Good. That is semi-supervised. Any typical example that you can think of in real world? Google Photos. I'll tell you the example. Google Photos. If you remember, or if you might have seen that, you create up a folder. If you're using some Google app account, you create up a folder, let's say my birthday, put up certain pictures into it. It will automatically tag some more pictures from your machine and find out and put that into auto created folder. Have you seen Google create some folders automatically for you? You have never created those, but you labeled certain images, and because of that label, it is creating them automatically. Now, that's a semi-supervised approach, wherein you are giving some label to small chunk, not for everything. Other things are automatically labeled by because of that label. That is semi-supervised. Google Photos is a very prominent example of this. Now, reinforcement learning. See, many of you might be interested to know about reinforcement learning a little too much, but I'll start with the part that this is a concept that was actually started way back in 2006, 7, 8, somewhere around that part, right? It was actually dealt with at that point of time, and it went into the dump yards for a very long period of time. But of late, it has started picking up again. In recent years, if I say 1.5 year, it has taken up the valuation again on the top, right? So reinforcement learning is coming back to the market, but it was into the slump for many years, right? So what does reinforcement learning do? I'll give you a small little idea to understand. It is a kind of approach wherein I have two things. I have a state, we call that as a state, and I have an action, two things. And we create a table of states and actions, right? There's a table of states and actions, right? So there is a table of states and action. For let's say state 1, action 1, what is the outcome? Let's say I reach to state 3. For action 3, I reach out to state S4, whatever, right? So there is a table that we generate into this. This table is not generated by us, it's generated by the machine for itself. How it is generated, I'll talk about this. But into that table, it gets to know that if it is in a particular state and takes a particular action, it is going to reach out to a different state, or may not reach out. It may remain in the same state as well, possible, right? Does not make an impact. But doing that action, is that an action that is rewardful for my goal to be achieved, or is that a punishment or penalty for towards the goal? That means something that is taking towards me towards the goal, that is a reward activity. Something that takes me away from my goal, that is a penalty for me, right? So what it does is it tries to create up that understanding, or creates up a set of or sequence of states and actions and their consequent result, whether it's a reward or whether it's a penalty to do for achieving a particular goal. And that is what it is overall done in a reinforcement learning. We have states and actions called as Q star. There are multiple algorithms into it. in reinforcement. We are not covering this topic in this course, to be very precise, setting your expectations right. But I would like to show a video to you guys. Okay, team. Was the sound audible? Okay, great. So listen to this video. Beautiful thing to learn. It's a very old video, 2008 video, but you will see some prominent names into this too.
So what you're seeing today is by far the most difficult aerobatic maneuvers flown by any computer-controlled helicopter.
The goal is always for us to take really hard problems that humans are very good at solving. For instance, Garrett can pick up any helicopter, even ones he's never seen, and go fly amazing aerobatics. So the question for us is always, why can't computers do things like this? So our goal is to build software that can learn to go fly a helicopter the way that a human being can, and that way we don't need so much engineering effort to build control systems like this.
So the basic technology used to develop the helicopter controller was a type of AI algorithm, type of artificial intelligence algorithm called apprenticeship learning. What the helicopter does is it watches a human pilot fly the helicopter around for a while, and by watching a human pilot learn to fly, it then learns to fly by itself. And so what it does is it watches the person fly, and then it will try to fly the same stunt maneuvers by itself, and maybe try a few times until it sort of nails the maneuver. And what you're seeing is the end result of this machine learning process called apprenticeship learning.
So basically what the software does is it acquires all of the measurements off of the instruments, and then it puts them into something called a Kalman filter that figures out where the helicopter is, which way it's facing, what its velocity is, and so on. And then that information is fed into a control system that decides based on where the helicopter is and where we want the helicopter to go. The controller actually computes new controls to send out to the helicopter every 20th of a second.
What we do is we collect several demonstrations from our expert pilot, and then our algorithms process these demonstrations to figure out what would be the ideal version of, let's say, a flip or a roll or a loop, etc. And then we use that as a specification for our control problem. And this allows us to find trajectories that are better trajectories than the pilot can demonstrate.
The helicopter doesn't want to fly. It always wants to just tip over and crash. So you always have to be maintaining the orientation of it. Whereas an airplane, if you let go of the sticks, it would more or less fly fairly straight. I've never seen anything like this done. The only autonomous helicopters I've seen are just they're hovering waypoints and doing quite basic maneuvers.
In order to make these applications work well, in order for us to trust helicopters and these sort of mission-critical applications, it's important that we have very robust, very reliable helicopter controllers that can fly maybe as well as the very best human pilots in the world can. And the work you saw today, I think, took a large step towards achieving that.
This was one of the experiment things that was being done by the father of machine learning. Now I'll say that he is considered to be a father of machine learning, Andrew Ng, one of the very prominent name. He was in the field of machine learning. Beautiful things written by him. If you ever get a chance, though a little bit complex in terms of language, but yes, beautiful explanations to the algorithms written by Andrew Ng. If you can read his material, it's available all over the internet. As a reference, you can read it. So that was a typical example of reinforcement learning, wherein a helicopter was looking at the maneuvers done by another pilot and start learning those things. And because once it has learned those things, it has created a sense of understanding that if I have to do a flip or I have to do a rotation, then what actions, what sequence of actions I need to take it in, right? Then came deep learning into the picture that demeaned the reinforcement learning concept. But then came in 2025. What was its name? Deep Blue? No. DeepSeek. 2025, DeepSeek came in China, right? So DeepSeek was essentially a model which was primarily based on reinforcement learning. It has a less of deep learning concepts, more of the reinforcement learning concept. That began again a discussion in our fraternity that is reinforcement learning the go-to thing. And essentially, if you ask my personal opinion, yes, it is a go-to thing, but it's slightly complicated, not easy to implement, not easy to compute. We have certain fixed algorithms into it, which are very, very complex. Maybe if I have another batch with you on reinforcement learning, that's another topic, might rather take 40, 45 hours. Reinforcement learning in itself. It's a very deep concept, right? So maybe we will see you guys in reinforcement learning some other day. But in this course, we're not covering reinforcement learning. Are we good? So that's a typical example. It has a raw data from the environment. It learns what algorithm to choose and then try to find out the reward and penalties and get the output generated. Reinforcement learning, typical example it shows is YouTube. I tend to slightly disagree on that because YouTube does use reinforcement learning to some extent, but more or less it is based upon deep learning concepts of recommendation systems, not exactly reinforcement learning only. Another example quoted up, self-driving cars, not reinforcement learning, search engine recommendations, autocorrect tools, games players can play with the bots. Most of them are implemented through deep learning in current scenario. Yes, they are a concept that you can implement through reinforcement learning as well. Implementation through reinforcement learning is still in progress. I will not say that it has been achieved, but same concepts that you see on my screen right now, they are achieved through deep learning already. We have already achieved all those things through deep learning. With reinforcement learning, it's still in work in progress. I will say that. Coming to the last or end towards the end of this particular presentation, I'm going to talk about some Python packages or libraries which are important for me during this course. Some names are displayed on the screen, some names may not be displayed up, right? So very important, these three libraries, NumPy, pandas, and Matplotlib, I have already requested that each one you should be aware about at least NumPy and pandas. Matplotlib, yes, okay, I can think of me not be aware, and I can think of that, okay, you can think of EDA section is avoided out. I will try to avoid if required the EDA part so that we can save time onto EDA part. And if you want me to do EDA, I'll do that too, no problem. Then this comes two libraries which are important. One is SciPy, another one is scikit-learn. These two libraries, I'm not expecting you to know everything about them, but maybe if you are aware, well and good. If not, I'll take care of that. Apart from that, I'll also use stats model, right? And there are some more libraries that will come in picture, right? Small little packages. So as and when they come into the picture, I'll talk about them. But majorly these three libraries, SciPy, scikit-learn, and stats model. Good. Some of you might be aware about stats model because you might have used that in mathematics course. If you have gone through ANOVA, chi-square tests, you might have used stats model in SciPy before. Scikit-learn, not many one of you would have used it. Great. So give that a quick read. Machine learning refers to the ability to learn from data and replicate human behavior. I tend to slightly disagree, not only just replicate human behavior, because not every time a human can activity is associated with machine learning. That's more or less into the deep learning concept. AI includes machine learning, deep learning, and each with the unique ability of simulating intelligence. Good. Which example illustrates the use of machine learning to enhance customer experience in an e-commerce company? Again, very basic thing. Even if someone follows the process of elimination, it's Yeah, it's C. It's a use of neural network with multiple layers for complex pattern recognition. Small little basic agenda that I'm going to cover up in this particular sheet for us, where I'll talk about what is supervised learning, what are different categories of supervised learning. We have two: classification and regression. Then where is supervised learning being used in the current scenario? And then we'll talk about the names. I'll only talk about the names of some supervised learning algorithms. I will not talk in detail about those algorithms right now. We'll discuss them in detail one by one. Good. Great. Now, would like to since it is day one, and we are going to start up with some more theoretical things. Confirmation, Manjanath, Mrudula, or Mrudul, sorry. Great. So let's begin. So we're going to start off with we will start with the supervised learning part, and I'll start introducing you what is supervised learning. We have already seen what is supervised learning, given you a small little idea about what is supervised learning. So it's a kind of approach, I will say that. Team, is that readable? Maybe to this one. That may be a little bit more better. So when I talk about supervised learning, right, it's a kind of approach, or it's a branch of machine learning wherein I am trying to make my machine, right, or where my algorithms are going to learn from a labeled data, right? I will have inputs, I will have the outputs, and I'm going to put those inputs and outputs to an algorithm. The algorithm is going to learn from that data and generate my model, right? That would be a basic idea about supervised learning. So it's a type of supervised learning is a type of machine learning where the algorithm learns. Now, when I say algorithm, that means these are predefined methods that we have, right? We learn these algorithms one by one, learns from labeled data consisting of input output pairs. In supervised learning, what we do is in supervised learning, we train the algorithm. We train the algorithm on a data set that has or that includes features, means the columns that contain the inputs, right? What would be the objective? The goal is, I can put up the goal here as well. The goal is to map the relationship or the goal of the algorithm that we have. Or essentially, you can say the model, right? Algorithm is to map the relationship between input features and the output labels. And this relationship identified So the relationship identified can further be used, to predict or make decisions on unseen data. So something that is not there, right? Or new data or unseen data. That is typically what is supervised learning that we have as a part of introduction. I can say that. Let's talk about the categories of supervised learning. Majorly, there are two categories, right? So there are two categories. Of supervised learning based upon the nature of the target variable, the target or the column or output, whatever you want to say it as. But usually the word that I'll use is the target variable. Good. Based upon the nature of the target. So what kind of target variable nature we are talking about, right? So there are two types of problems that we solve. One is called as a regression, and the second type is called as a classification. Good. Two types of problem. Now, what is regression and what is classification? Let's understand that too. Good. So for that purpose, we should know what is a continuous value and what is a categorical value. How many of you know what is a continuous and what is categorical? Because that becomes your base to decide what algorithm that you're going to use to solve a particular problem. So you should be very much clear about the thought process about what is continuous and what is not continuous or what is categorical. So let's try to think about a data for a moment, right? Categorical that we countable, we can't count continuous. Uh, okay, so let me just break it down. Categories, group. Okay. If I talk about the data, right? If we talk about the real world data, in data, if I talk about data I can divide into two sections. Either the data will be in a number format or it will be in a text format, right? Usually, right? Either I'll have numbers or I'll have text. Agree to that? Yes or no? Great. Now, when you talk about number, the numbers are divided into two categories, right? Numbers have two categories. One we call as a continuous number, and second one we call as a discrete number. When you talk about text, text is usually classified into categorical nature only. Good. So that is the basic ideology behind the segregation of data. But what is continuous, right? So continuous is that data. Please understand it. Continuous are those numbers where there is a possibility of a number or any value between any two consecutive values. For example, let's say think about a school, right? Let's think about a school as a common example, right? If I talk about a school and let's say I have some number of children in my school, good. Now there is a child of age 3, there is other child of age 4, right? Is there a possibility? Let me ask you a very generic question. I'm talking about their ages right now, right? So there is a child of age 3 in my school. There is a child of age 4 in my school. Is there a possibility that I have another child in my school who is between 3 and 4? Is there a possibility? Right? Or what is the possible numbers that I can have in between 3 and 4 in terms of ages? How many numbers are possible? Not just 3.5. That is just one example, Suleiman. 12, 9. Essentially, what I'm trying to ask you is, what is the possibilities of numbers in between 3 and 4? If you think about ages, I can have people practically possible. Only 12. If there is a child of age 3 and there is a child of age 4, I can have a child whose age is 3.01. There is a possibility that I have a child with 001 or 0001 or 000001. Essentially, if I talk about, there is a possibility of infinite values in between 3 and 4. I can go to their time of birth, in seconds, milliseconds, nanoseconds, femtoseconds, petaseconds, whichever level we can want to go up to. Essentially, I'm not saying that there will be a value. I'm not saying that. I'm saying that there is a possibility of having a value. Correct? Or in simple terms, for anything or any particular feature, any particular column of the data, if there is a possibility of values or between any consecutive set of values, there is a possibility of infinite values, I will say that is a continuous number. Usually these are measured quantities, right? When you measure certain things, you say that these are continuous numbers, usually. For example, let's take about another example to talk about continuous numbers. Let's talk about weight. Let's say I weigh somewhere around 72 kilograms, close to 72 kilograms. Or there will be some person who might be weighing 7. If I go to very, very high precision, possibility of 72.00001 as well. Do we agree? Right. So certain quantities where things are measured and there exists a possibility of having infinite values between any two consecutive values, I will say that as a continuous quantity. Good. Then comes the discrete quantities. Right? In numerical, I have talked about two things. One is numeric continuous, and second one I talked about discrete numbers. What are discrete numbers? Discrete numbers are again numerical quantities, right? But they have a finite value, finite and fixed values. Let's talk about an example, right? For example, let's say you roll a die. When you roll a dice, what you will get? You have 6 choices. Either you will get 1, 2, 3, 4, 5, or 6. Is there any other possibility? Is there a possibility that I can get a 1.2 or 2.7 or 3.4? Is there any possibility of having a value between 1 and 2, 2 and 3, 3 and 4, 4 or 5? There is no possibility, right? I'm still getting the numbers, right? I'm still getting the numbers, but these are discrete numbers. Discrete numbers means that there is no possibility of having a value in between any two values. Taking the school example, right? If I say that my school has 100 children, or I will have 101 children, I cannot have 100.5 children. Is it possible? Can I have a value in between? No, right? So things which are counted, usually counted, right? Countable things are usually called as discrete numbers. Countable things, countable numbers are discrete values. Good. Remember, it has to be discrete means these are finite. It can be a finite set of values. It can be an infinite set of values as well. I can have long numbers, long list of things. But in between two consecutive values, there is no other value possible. Good. that is called as a discrete number. Are we clear? So when I say categorical, categorical essentially means that I am representing a category. That means I have fixed values, right, which are not numerical. Usually not numerical, they can be numerical as well, right? So let's say, for example, days of the week. I can have Monday, Tuesday, Wednesday up to Sunday. Good. There is nothing possible in between. Right? I have fixed finite set of values which are in text form. I will say them as categorical. At times, listen to that very carefully. At times, I will represent these categorical values in form of numbers. If you want, I can include LGBTQ as well, but that's not a different gender. We have these three genders. Good. Now, I might represent the data in the form of MFT, male, female, and transgender, or I might also represent them as 0, 1, and 2. Both of them are categorical right now. They are representing a category. Make sense? So it depends upon the nature of the data to decide that I may have numbers, but they might be representing a category. Are we good? I may have text, but that may not be representing a category. Can you give me an example where there is a text and not representing a category? A real word thing? Anybody? Suppose I collect the list of names of the students that I've ever taught, the names of the people. Let's say I get 1,000 names. Each of them are different and unique. For example, the number is going to be get more than 15 to 20,000. More than that, people have been gone under my belt. Right? Suppose I have 10,000 different unique names. Does that mean these are names are a category? These are text, right? So not always a text is going to be a category. Remember. Good. Names is not a category. Is it? Because there will not be a finite list. It is not a finite combinations of values. That means I have 10 names, 20 names, and all names will follow in that category itself. No. That was the last PPT that I've shown up. Any more questions on categorical and numerical on continuous? So let's talk about regression. So what we decide in regression is when my target variable, where the target variable is continuous. So if my target variable is of continuous nature, right, the prediction task is regression. So when I have a target variable which is of continuous nature, I will say that as a regression problem. Example could be prediction of house price. We'll work on this data, house price data, right? Or let's say any random numbers, any random picking up things. Let's say prediction of diameter or prediction of temperature. If I'm predicting what temperature it's going to be, so it can be 32 degree Fahrenheit, it can be 42 degree Fahrenheit, it can be 41, 41.001, could be anything, right? I can have any continuous value coming in between for temperature, or degree centigrade, whatever you want to say that as. Good. So that is regression task. Prediction of a car price. Yes, you can say that. On a similar note, I can talk about classification, same level. When the target variable is categorical. Please remember team, categories can be represented as text, they can be represented as numbers. We need to think that what we are trying to predict, is that a category or not? We need to decide the nature of the data. Good. So when the target variable is categorical, the prediction task is classification. That will be our topic number 2. We'll start with the regression first, and then we'll delve into the classification. At least mathematically it would not be possible. Great. So we have seen what is target variable is continuous, means that when we will get a data, right, that data is going to be in the form of a data frame, right? We will have a data in the columnar form, right? One of the column will be decided as the target. Target means the column that I wish to predict. I wish to predict a category, or I wish to predict a continuous data. So we need to take up a decision or call. What is the nature of values in my target column, Kishore? If it is a continuous number, right, then I will think of regression. If it is a category into that, I will think of a classification. It is a numerical value, which is not a category, right? It's a continuous number. Then I'll use a regression problem. Good. I hope that makes it clear for everyone. Great. So I will not delve into that too much. I have a picture for you guys. Let me just show it. So typical example of temperature. Accordingly, either hot or cold based upon temperature value again. But you're not telling me the temperature. What you're telling me is the nature of the temperature, right? It is hot or it's cold, as Suleiman has. Good. Let's quickly walk around with the applications. I will just only talk about the names of the industry. And you guys will tell me the examples. Because these are some day-to-day things where you might have observed. Let me talk about example number 1, HR operations. Do you think that there is a role of machine learning in HR operations? ATS, many of you would have observed ATS. Great. In the field of finance, essentially there is no other field, no field where machine learning is not present. Emails, whether email is a spam or not a spam. Manufacturing. Other example, maritime industry. High tide, predicting tide's value, whether it is a high tide or a low tide, that can decide which way I want to take up my cruise or the ship. Any kind of incident management, if there is a prediction of maritime icebergs, I can avoid Titanics. Agreed? Weather forecast can be a part of it. Identifying a picture of dog, classification. But usually through a picture, we do not do it through machine learning, Pragati, we do it through a deep learning concept. But it's a classification. Fraud detection, stock market price prediction, regression problem. That can put into we can put that into finance category. Some examples, I'm not saying this is the entire thing in the world. There can be a lot of things which are more than this. There can be a lot of industries where I have machine learning algorithm available. Emails, identifying emails as spam, not spam, is classification. I have two categories of emails. It is a classification, right? So these are typical things. Last but not the least, I am just putting up some commonly used algorithm names. The commonly used algorithms in supervised learning are we have linear regression. That's the one that I'm going to start with. We will have logistic regression. We can have naive Bayes. We can have k nearest neighbors. Usually known as KNN. We can have decision trees. We can have random forests. We can have support vector machines. Commonly known as SVMs. So this is, I would say that these are the names of the base algorithms or the kind of algorithms which are commonly used, right? And we will walk around with each of these algorithms, their intricacies, their mathematics, one by one. It is going to take almost like entire course time. But apart from this, majority of the time will be spent on this. But apart from this, we will also learn how do we create algorithms of our own, right? For example, we'll learn how to create algorithms like you might have seen algorithms in supervised learning. I will talk about, let's say, supervised learning algorithms. You can think of gradient boosting machine, right? You might want to know about extreme XGBoost model. You might also want to know about, let's say, the ADA boost model, adaptive boosting. So these are some common names that you might have seen over the internet or some, but these models are actually not individualistic. They use some of these basic models, right? So understanding these first 7 models is really important, right? If you understand these, going through with advanced models like GBM, 60 boost, ADA boost is easy, right? Because this is just a kind of arrangement or kind of ensembling that we do with the or arrangement of these models that I do up in order to create these models. Nothing new into this, right? So these are not some separate entities. They have a separate thing of their own. These are just a combination that I have arranged up in a different manner of these basic ones. So understanding basic one is more important. Then you'll understand how to club them together. When you club them together, what you create up is advanced models. Good. If you ask me what would be the common use case, Linear regression, I can have a common use case, let's say prediction of house price. Logistic regression, I can say any kind of classification where I have a binary data to be predicted. That means I have yes or no choice. I have good or bad choice. Buy will not buy choice. Like let's say for example, customer churn. I am selling insurance policies, whether a person will buy or not. Knife base I can use for, let's say, spam detection. In emails, I can do that. I will use a common use of KNN is healthcare. Why healthcare? Because this is an algorithm that is based upon the nearness or how closely the values are, right? So what we think of is that if there is X who is affected by one particular disease, then potentially a person close to X will be potentially have higher chances or higher probabilities of getting affected. That is basic ideology behind KNN. We'll discuss that in detail. What is the idea? Decision trees. Anywhere I have a rule-based decision-making process. I am taking a decision, but that decision is based upon certain set of finite rules. So rule-based decision-making process, I will use decision trees. You are not going to create the rules. Rules will be generated by the machine. But we want to do that based on the basis of rules. Random forest. A typical example is credit scoring. When I have to do credit scoring or some kind of things. That is again rule-based kind of thing, but with multiple numbers of things to be taken up together. Support vector machine. We generally use it in social media monitoring. Possibility. It depends upon the nature of the data, how good or bad quality data that I have. Sensible? Essentially, whatever the name of the algorithms that I've put down here, we will walk around with all of them. But in unsupervised learning, we'll have some more algorithms. If I talk about in totality, you will learn about somewhere close to maybe more. I exactly do not know the number. I might introduce you some other algorithms which are not part of a standard curriculum. In this course, will you cover how to build the algorithms or how to modify the existing algorithms? In this course, I will talk about algorithms. Okay. Okay. Shall we begin? We want to talk about supervised learning, the regression techniques, and we'll start our agenda. We'll start with the agenda. What is in store for you in this particular file? This file is going to be continued for next 2 or 3 sessions. I'm pretty much sure. It might take a little bit more longer than that. Right? So we'll start with the types of regressions. We'll not again restart building up what is regression and everything. Not required. Types of regression. And the first type of regression that I'd like to talk about is called as linear regression. Within that, I will talk about the simple linear regression. And we'll build the first concept of scikit-learn, that is train test fluid over here. Yet, then we'll talk about multiple linear regression. Within that, I'll try to build up a concept of overfitting and underfitting. which attracts another concept, that is very common thing, bias variance trade-off. So little expectation about the statistics team. We will deal with a lot of statistics and mathematics. So there is a small little preparatory course on basics of fundamentals of mathematics and statistics, right? I hope so you guys have gone through with that basic understanding, right? I need to know, you should know what is normal data, what is not normal data, these kind of things. Which is non-linear regression. It's a big agenda team. Within that, I will talk about polynomial regression. So that will be types of regression done. Then we'll talk about model evaluation techniques, model evaluation and validation. We'll talk about cross-validation techniques. We essentially will have 2 or 3 techniques in there, basically 2, k-fold and then we'll talk about the performance matrix. Essentially these performance matrix that I'm showing up right now, writing up, we would have the explanation of these right before we come up to this point, right? I would have to use these performance matrix initially itself in order to make you understand what is linear regression. So performance matrix for regression. There I will talk about number 1, mean squared error. Now some of you might find them as known terms. We'll talk about root mean squared error. Commonly known as RMSE. Then we'll talk about mean absolute error. Commonly called as MAE. And we'll talk about R squared. Very important term in terms of regression. R squared, we call it R2. Usually called as R2. R2 score. Okay, beyond this, we will talk about some regularization strategies, the regularization techniques. Long agenda team. I will have 2 techniques that I'd like to talk about. One is called as lasso regression. And we'll talk about very important terms. Again, you will see the usefulness of these things at the later stages when you will see regularization being used, lasso or L1 regularization and L2 regularization. I'll introduce you what is L1 and what is L2 later on. Then this part is not typically for the linear regression or the regression problem that I'm going to solve up, but this is going to build up our concept. This is a model optimization technique, I can say that. And this is called as hyperparameter tuning, which is actually applicable everywhere. It is applicable in regression, it is applicable in classification as well, or in other types of modeling approach. So hyperparameter tuning, I will talk about grid search CV model. After this, I will talk about pipelining. And we will look at scikit-learn pipeline, sklearn pipelines. So essentially that would be the thing that I'll cover up in this course. this but not course, but this particular topic, which is supervised learning regression. Now, I would want team you to go through with whatever agenda that I have written down, right? Just go through it once. If you feel that in terms of regression, some of you are already about machine learning or have used machine learning in the past. So I would love to have some more inputs. If you think that there is any particular topic which is missed out, you can let me know. Anybody else? Anything that you would like to bring into the picture or onto the table? Put that into the chat as well. So when I talk about the types of regression, this is where I told you that I'll start off the things with. I have not talked about what is regression. We have discussed that. So predicting upon continuous data is regression. How we are going to predict it up, that's a separate thing, right? Where do we use it? Almost everywhere, right? I can use it in oil, gas, marketing, retail, healthcare, real estate, anywhere I can use it. So types of regression will start from that point. So a regression can be classified into two categories. So regression types can be classified in two categories. Number one, we call it as a linear regression. And the second one is called as non-linear regression. What is the typical difference? In linear regression, what we do here is linear regression, the objective that in linear regression finds a straight line relation. Straight line relationship. Now that may not make sense as of now to many people. A straight line relationship between the dependent variable. When I say dependent, that means the target variable. Dependent variable, or that you can say target, and one or more independent variables. When I say independent, that means I am talking about the features, independent variables. That means features. I can have single feature or I can have multiple features as well. Good. What does non-linear regression do? It is also going to use find the relationship between that dependent variable and independent variable, but in a typical more complex shape. It will use a little more curved shape or curved lines or complex shape structure, not a straight line. Now, very important to understand what is that straight line relationship and how does it make an impact. We'll discuss that, but let me put up non-linear regression finds the relation, finds the relationship between features and target using a curved or more complex shape. If you guys have gone through with EDA and might have studied about regression plots or reg plot in Seaborn, or might have seen that in joint plot, a straight line that is putting across the relationship or defining the relation between the two variables, right? You might have seen those things. So we'll try to build up that line. Okay. So we'll now jump on to the linear regression. That's the first category that we need to deal with. Let's start with linear regression. I have some theoretical notes onto this. I will just copy paste those. Would that be okay? I'm not looking forward because I have 12 minutes left out for the today's session. Not looking forward to build the concept first. Right? I want to build up the concept of this that might be useful for you. So linear regression, as the name suggests, it tries to identify. It's a supervised machine learning algorithm that is used to predict a continuous variable, right? A continuous target variable, and we will try to do that prediction using a straight line equation. Very simple logic. That means, look at this. Suppose I have a data, right? A simple data. I'm talking about, let's say, one independent variable, and this is for the ease of understanding, right? I have a data that contains two columns, a column X and a column Y. I have named them X and Y because there is a certain reason behind it. Later on, when we start with scikit-learn, you will understand why X and Y. Where X is my independent column or my feature or my input, and Y is my target. So my job is that if someone gives me, this is a given information to me, right? I have, let's say, 100 rows of the data, where for a particular value of X, I know the value of Y. This is given to me. Now, there can be 101th value where I do not know what is the value of Y, and I want to predict what is the value of Y going to be for that 101th term. Sensible? Now, this Y is of continuous nature. So what I can do here is, I will take those X and Y and let me just plot a simple scatter plot. So I'll take X on X axis and target Y on Y axis, and I can plot a scatter plot of this. Right. I will have certain dots. let's say for all the randomness in the world, I have put down the dots. Now, do you get this in this point? Simple logic, right? For certain values of x, I have certain values of y. Accordingly, I have plotted up that simple scatter plot. Now, what does linear regression suggest? That if I have to establish a relationship between y and x, what I want to do here is I want to get the value of y. How? By a function of x. That means there is some explanation that I can give about y using the value of x. Does that make sense? Right. Now, how that function that I'm going to use to explain y. In linear regression, that function is a straight line. In linear regression, that function is a straight line. So if I just try to drop a straight line for you here, let us suppose this straight line represents that relation. Good. That this is the line. Now this is a straight line that is showing up the relationship between x and y. Agreed? This particular line makes an angle here. Let's say this angle is theta with respect to the x-axis or my input variable or independent variable. Good. It makes an angle. So if I have to geometrically represent the equation of this line, I can represent that equation as y is equal to mx plus c. Seen that equation before, team? Maybe in your schooling days, right? So what is here? There is two terms that are coming up. One is called as m and there is a c. Because we know there are certain values of y and certain values of x which are given to us. We already have those two terms. What I would now need is that line. This line is having, so if I can find the value of m and c, right, then I will have that line equation. So we should know what is m and what is c. So this word m is called as the slope of the line. And the c is called as the intercept. See, I am using the terms of geometry right now. I will later on change these terms and I'll use the terms which are used in regression. Good. I'll tell you what are those terms. So if it is slope and intercept, can you tell me what is this, how the slope can be measured? The slope is always given as tan theta of an value. What is the slope of this line? It's the tan theta there. So theta is the angle that it makes with this axis. So the slope of this line with respect to x is tan theta of this angle, or is the tan value of this angle. Can we get this tan theta value anyhow? Anybody? Anyone can tell me, how can I get the tan theta value? Let's say in this equation, in this scenario. Very easy it is. You can take up any two random points on that line. Let's say suppose I took up this point and this point. Draw a horizontal line like this, vertical line, draw a horizontal line like this. This angle is also going to be theta, correct? And we know that tan theta is equal to opposite side by base, perpendicular upon base. So I can measure that distance. I can measure this distance. And I can get the tan theta. Or you can say that it is y2 minus y1 upon x2 minus x1. Do we agree? But second thing that we have in the equation was C. C is called as the intercept, or intercept is the point at which the line cuts the y-axis. So my point is here. So the distance from x-axis to this height is C. The point on y-axis where the line cuts the y-axis. Are we good? Or essentially, if we put into x value as 0, you will have y is equal to C. Correct? So when my x-axis becomes 0, y becomes equal to C, or intercept. Or essentially, in other words, it's the value at which the line cuts the y-axis. Does all this make any sense to you, anyone? Whatever I explained? I have given you the agenda. Typically, what is the agenda for the sessions? That is about the supervised learning regression techniques. And we have types of regression, what is linear regression, and the simple linear regression, multiple linear regression, and so on, going on with non-linear model evaluation, and so on. That was the agenda that I have discussed. Beyond the agenda, I have just given the different types of regression. What are the different types? So there are two types. One is a linear regression, other one is a non-linear regression, right? So when we find out a relationship between independent variable and dependent variable through a straight line equation, we say that as a linear regression. If it is non-linear relation, or I can say that it's a curved relation or any complex shape relationship, I will say that as a non-linear regression. Right? And then I try to showcase an example of a regression. What exactly is the objective that we try to fulfill? So I'll start back again from that same point. All right. And let me just put up some real world perspective to it. Okay. Let us imagine that you have a data, a very simple data. I love fruits, so I'll take some fruits example. Suppose you have a data that is given to you, a simple data I'm taking up, where you have an information about the quantity of the fruits being bought and the price being paid. Right? There are only two information, a quantity and a price. Good. Let's say on some given day you bought a quantity 3, you paid a price 7. On some other day you bought quantity 2, you paid a price 8. Some other day you bought a quantity 3, you paid up a price 9. Another day you bought a quantity 4, you paid up a price 10. Then some for 5, you paid up, let's say 7. Or let's say for 6, you paid up 12. Or could be something like that. Good. Very simple data. Now, let us assume that the task that you have to complete is that what is your objective? Your objective is, what if I buy a quantity 7? How much money would I be paying up? Are we good? Very simple data, very simple perspective. Let us now try to formulate that data into terms of a graph. I have two values, one is a quantity and other one is the price. Good. So I'm going to plot up a simple graph, a very simple scatter plot, right? Where I will take quantity on y-axis, on x-axis, and I'll take price on y-axis. Try to understand, team, that this is an example with smaller chunk of data to make you understand the concept. The real picture will have a lot of amount of data, so that the picture will look slightly different. Good. Let us try to put up those points. So when x is 3, let me put up the lines first. So let's think of this is 1, this is 2, this is 3, 4, 5, 6, or maybe 7. And then I can think of here, maybe 1, 2, 3, 4, 5, 6, 7, 8, 10, 11. In my team, this is not to the scale, so please allow me with that part. I am not very much expert in that. I can plot up a scaled graph as well for you if you want, but that will not make any sense. Okay, let's try to plot up certain points. So when the first point, when X or quantity was 3, the price was 7. So I can think of 1, 2, 3, 4, 5, 6, 7. So here, good. When it was 2, it was 8. For 2, it is 8. So somewhere here, another dot comes over there. Then for 3 again, I have 9. I have 9 over there. Good. Then 4 for 10. I may have a point over there, somewhere around. Then 5 for 7. Maybe here. And for 6, I have 12, maybe somewhere here on the top. Good. So these are the points as per my data. Is that okay? Now, what we would like to look at, we are looking at, I'm going to remove this picture, not required anymore. We have got the points. Good. Now, what is my objective? My objective is that I want to tell the price. I want to tell the price. If I know some quantity, so I need a function in the terms of quantity. Mathematically, it has to be something with respect to quantity. Good. Because that's the only known thing that I have. I only know what quantity I'm going to buy up. So I have known thing. On the basis of known things, I want to find out an unknown thing. That's my objective. Is that I will try to establish this relation in the form of a linear equation. In the form of a linear equation. When I say linear equation, essentially it means an equation of a line. Good. So I can assume, as of now, I am assuming, I'm not telling why I'm taking that line. I will explain how will I come to that conclusion as well. Good. Let us assume that a particular line, let's say this line, depicts the relation between the quantity and price. In terms, what I am trying to say is that if you take price is equal to a constant M multiplied by the quantity plus a constant C. Good. Great. So my objective is to find this line. Try to understand. Your objective is just to find that particular line. And that would be your linear regression model. First algorithm, linear regression. If I can find out a way that is this the line that I want to take up. Because if you think about lines in this plane, in this graph, there are infinite line possibilities that I can have another line like this, or a line like this, or a line like this, or a line like this. There are infinite possibilities of line. Now, out of all these infinite lines, which line do I have to choose? That is the most important part, isn't it? Because there should be one line wherein I will think that this is my best possible solution. So I need to make a decision that which one of these lines is my best possible solution. Now, if I ask you that there is a problem P and you need to provide a best possible solution S, what would be your perspective towards the best possible solution? I have a problem P and I have multiple solutions to that problem P, then solutions S1, S2, S3, Sn, right? Then out of all those solutions, I will choose a solution that offers me minimum amount of error. Do we agree? What we expect is that each of those solutions is going to give me some kind of error, right? It might be 1% error, 10% error, 20% error. But out of all the possible solutions, I will look forward towards a solution where the chance of error or the amount of error is going to be minimal, whichever it may be. Agreed? Right? So your objective here is to find a line. Listen, in linear regression, I am going to find out a straight line that has minimum, or that gives me minimum amount of error. The question arises, how will you measure the error? Make sense? Because error measurement is important over there. Build up that the line that I have thought of. Let's say I have thought of a random line. I have not taken this now. This is a randomly created line. Good. Good. Let us now, since I have already selected that line, can I find out? Very simple question. Can I find out two important things? The first thing is the slope of this line, the theta. And the second thing is the intercept. Is that possible to find out? Easy thing. If it is not possible, let's say you cannot find it, I will start with a random value of slope. I have chosen a random slope, right? And a random intercept. I will start with a random slope value and a random intercept value, right? Because I am choosing a random line, that means I have chosen a random slope and I've chosen a random intercept for it. And I've randomly drawn a line. Good. Because since I've already chosen a slope and intercept, that essentially tells me that I have a line and that has an equation. Y is equal to M, which is my slope, X, which is my input, plus C, which is my intercept. Good. Now remember, I currently know the value of M and C. Why? Because I have randomly chosen that value. So now I know this line. Do we agree? Yes or no? I can just say, for example, M is 3, C is 2. For example, I can put up any random value for X. I will get a value of Y. So 3, so for when X is 1, Y is 3 into 2, 5. For X1, Y 5. Could be a point. Randomly chosen, right? So I can find out 2 points and connect those 2 points and create my line. Easy. Good. But I still do not know whether that is my perfect line or not. Agreed? Now, how do I check the error? So what we are doing over there is, I am going to make predictions based upon this equation of line, right? I'm trying to tell it that this equation of line is a representation of the relationship between my target variable Y and input variable X. This is what we are saying, yes or no? Now, so in terms of understanding, so that we can differentiate well, and in terms of the architecture or the nomenclature that we follow usually, I will represent the results of my predictions with a hat symbol. So I will say my prediction is Y hat is equal to MX plus C. And for the actual value of x, whatever is my actual given data for y, I will take that as original value. So without hat. So y without a hat. Let's say, for example, we had the first data point here when this 1 point, right? Let me just take up a line tool. When x was 2, right? Y was this. Agreeable? This is the given information to us. On that basis, we have got this data point plotted up. Correct? Now, for the same value of x, when x is equal to my predicted value y hat is equal to, if you look at that very closely, it's this point on that line. Correct? So let us assume that value is 6. This is an assumption, team. Just an assumption. I'm not saying that this is not to the scale, and I'm not actually solving. This is just an assumption, and I'm assuming the values. Good. So what I can say here is that I'm putting that with a red dot here. When for this particular, so brown dot that you see over there, this is your actual value, and the red dot is your predicted value. Can I say that? Good. Not maybe exactly there. Maybe a point here, point here. Okay. So if you look at that, my all predictions are lying on the straight line, the red dots. Make sense till now? Yes, no, maybe. Now, what is my error? My error is, look at the first answer. I was supposed to predict this one as 8, correct? But what I predicted is 6. What did I make the error as? My error can be now given as the difference between the actual value and the predicted value. So can I say this is my difference over there? This is my error, isn't it? So does here. This is your error. This is your error over there. This is your error over here. This is your error over here. This is your error over here. Now, lines are that should be vertical, should be in parallel with the y-axis. Please pardon my drawing. Are we good? Great. Now I am going to put up some value. What is that amount of error? The amount of error, I can quantify that by subtracting my actual value with the predicted value. So actual minus predicted. That is your quantified value for the error. So I can say, let's say, actual value 8, predicted value 6. So my error is +2 over there. Let's assume that is +3. This is assumption team. Let's say this is also +3. Let's assume this is +3 again. Assume this is -7. Let's assume this is -4. This is our assumptions, all assumptions. Good. You might say that it does not look like that. Great. Now, if I ask you in a very simple manner, correct? Let's put up a counter variable I, y hat of I, y of I minus y hat of I. And what we are taking is the summation of that. Do we agree? Great. And if I ask you the average error, you will divide it by the number of elements, n. So I is equal to 1 to n. In my example, it is saying that if you solve this part, you will get an average error as 0. Because average error 0 means you're doing a perfect job. 0 means 100% correct, isn't it? A 0 error does not mean 100% correctness. Now, I'm not saying that. In my situation, what we see is mathematically the value is 0. There should be some error. 0 does not exist. That's a separate thing, Manjunath. I can create certain models where you will get 0 errors. It is possible to create such things. But point is not that as of now. My point is the calculation of error that we are doing as of now, the quantification of error that we are doing. Because the mathematical calculation or the average calculation of the error is telling me that there is no error or 0, right? But actually, when I look at this information, I see that there is a lot of errors into this. And why is that 0 coming up is because of the negative and positive nature of the error terms. I have certain errors which are negative. I have certain errors which are positive. So how can we control this? This is only happening because I have certain errors which are of negative nature and certain errors which are of positive nature. Yeah, more or less we can square the value. Either I will calculate my error as an absolute term, or I have a second choice where I can take a square of that term and then take a square root of it. These are two ways by which, in simple terms, you can convert any negative value to a positive term. So there are two measures by which I can put the error on, right? Number one is called as the absolute error. Absolute means I will not consider any negativeness or positiveness of the differences, or rather I will modify this equation as sigma I is equal to 1 to n. Instead of taking the sum of actual values, whatever the difference comes out, I'll take the absolute difference. Absolute difference means if result is negative or positive, I will still take it as positive term. Now, can someone quickly tell me what will be my absolute error in this? Average absolute error? Good, no problems. So, point is that if I take the sum of the absolute errors and divide it by, or take the average sum of the absolute errors, and right, we take the absolute error average, I will call this term as mean of the absolute error, or in short we call that as MAE. Did we get hold of it till now? Do we understand what is MAE for now? Is that okay? I have created the concept of one of the performance metric that we look at in regression model, which is MAE. And please remember, I am going to transform this to our ultimate objective to find that line. I have not yet reached to that goal. What we are trying to find out right now, the line with the minimum error, but I'm still struggling to find out how to find the error. Good. The second measure that I can use to calculate the error, as I said that we can also take the squared values. That means, suppose if I have this 2 of -4, So if I take -4, the square it up and put a square root after it, what I'll get is a +4, isn't it? So what I'm going to do here is I will take up the same error calculation formula that we have taken up earlier. Into this, I'm going to apply that what I want to do is take the summation of the squared value of the error. So y actual minus y predicted the whole square. Sum up the squared terms and take the average of it. So what I'll get is average squared error. What I'll get is average squared error. Isn't it? This will not be an absolute representation of the error, but that will be a squared representation, right? But I will have an average squared error value, isn't it? Or I can call that as mean squared error. That's the common term, or MSE. So if I take the square of the errors and take the average of it, mean squared error. If I take the absolute values and take the average of it, I'll say that as a absolute error. Is that okay for everyone? Now, if I just put up a square root over it, since these values are square terms, so I need to put up a square root on top of it in order to get the values to the same scale as I have the original data. So I can put that as RMSE, root mean squared error. We'll discuss RMSE slightly later. What is the role and importance of RMSE? That's not required right now. Good. Now let me ask you, which one of these two do you think is a better approach towards the error? Because I have given you two approaches to calculate the error. Either I can take up this average of the absolute values, or I can take the average of the squared values of the errors. What do you think is a better approach? I'm leaving the decision to you right now. Then I put up a hypothetical situation for you. Just 5 data points only, where I'm taking up only 2 columns in front of you. Because of some issue, this is my y actual value and this is my y predicted value. Good. So y actual is 1, 2, 3, 4, 5. Y predicted is 4, 6, 7, 9, 50. Now I want you team, this is, you might find that is not useful, but I want you guys to calculate, do the calculations for me, find out what is the value for MSE for this and what is the value of MAE for this. So that's going to be -3, -4, -4, -5, and -45. So only term I'll struggle with is square of -45. 2025 plus So my MSE value is 418.2 MSE. If you talk about MAE value, so that's going to be 7 plus 4, 11, 11 plus 5 is 16, 16 plus 45. That's 10.16. Now you might say that this is a squared term. So I can take a square root of it to bring it to the same level. That comes around 20 point something, because it's 480, so 20 into 20 is 418. So maybe 20.4, close to that value, not exact, but somewhere around 20.4. Good. Now, if I talk about the comparable ratios, I have 10.16 and I have 20.4. Now, I'll ask you a simple question. Look at the error values, these error gaps. I have -3, -4, -4, -5, -45. Which one out of the MAE value and RMSE value, which one do you think is a better representation of the error? Usually, if I talk about, if you think about the conceptual part, in terms of concepts, what I'll say here is the RMSE is a better representation. It is a better representation always than MAE. It's a better representation in terms of understanding the error. In terms of representing the error, RMSE is a better metric than MAE. Why? Is because the value of RMSE I can compare with MAE always. And if there is a significant difference between RMSE and MAE, that means my MAE value is lower and the RMSE value is significantly higher. That tells me very specifically that there are certain predictions which are not very good. They are going way beyond the rest of the errors. Certain errors are huge, because of which my RMSE value is getting higher, or presence of an outlier in my error. Or what in turn I'll get to know is that if there is a significant amount of difference between MAE value and RMSE value, I will understand it that in my predictions for certain input values, I am getting very exceptional or very out of the box answers. Or I can say that the MSE or RMSE values, these are sensitive to the outliers. These are sensitive to outliers in the data. And hence is a better metric in terms of comparison, right? Or in terms of understanding the errors in the data. Do we agree till this point? You can think of the same situation, just change that error. Similar situation. What if I just change that 0, make it 5, make that error as 0. You will notice that there is no significant difference between MAE and RMSE. So if data does not have an outlier present, the results does not have an outlier present, I will have very minimal or almost like no difference between MSE value and MAE value. If there is a absence of an outlier, and if there is a presence of an outlier, RMSE will always show us a better picture. Are we good on this point till now? Yes, no, maybe. Team, quickly. If it is not clear, ask it. All right, considering no input, is everything good? I want to look at beyond that information, right? I want to look beyond it. Similarly, when I calculate the error, right? Suppose there is some actual value, some predicted value. Good. What I'm expecting is a minimum error. This is my minimum error. Good. So for some data, I'm getting error in the range of, let's say, in the range of 10, up to 10, right? Up to 10, let's say 10 to 7. But for some value, the error reaches out to, let's say, 150. Rest of the errors are in the range of 0 to 10. Good. But this one odd error is 150. Make sense? Now, if there is some kind of error, this kind of error, would you not like to notice why is that error happening? If everyone is going in one way, why is something going in a different way? Right? And you would want to pick that up. You want to pick it up. Now, MAE will not allow you to understand that aberration, the presence of such kind of thing. Whereas with MSE, which is sensitive to this outlying information, I can find it up easily. That there is a possibility of such outlying errors. So always MSE or RMSE, you can say in either terms, because RMSE is comparable to MAE. That is why, because they belong to the same unit. Because MSE is a squared form, so not comparable, but MAE and RMSE are comparable. Good. So RMSE gives me a better understanding, better picture of the presence of an outlier or not. If MAE and RMSE value both are almost close to each other, I can assume that there is no presence of an outlier. Almost all the errors are in a finite range. If there is a significant amount of difference, let's say 20 and 20, double the error, or 1.5 times, RMSE value is 1.5 times the MAE value. There is definitely certain data points which are getting extremely wrong predictions, which I do not want. Make sense? So because of the sensitiveness to the outliers, we prefer MSE or RMSE model for calculation of the errors. We prefer that. However, when I am going to judge the performance of the model, I will look into everything. I will look into MAE, I will look into RMSE, I will look into MSE, and I'll also look at another metric called as R squared. So when I judge the performance, I will look into everything. But if I have to do some calculations mathematically, better representation is RMSE or MSE value. I will not put RMSE, but MSE, mean square error. That is a better representation. Why? One more reason coming into the picture. Why I would like to use MSE and not MAE? Okay, team. For this, I would like to bring again some more concept. How many of you understand differential calculus? I am not very bad at it, let's say. So I have an equation 3x plus c, or let's say 3x plus some constant number 2. Y is equal to 3x plus 2. A simple equation. Now I'll ask you, what if I do a delta y by delta x? I wanted to do a dy by dx. Will that be equal to 3? Acceptable? Now, what if I make this y is equal to 3x square plus 2? I've just made one change. Instead of a linear equation, I have made it a squared equation. Good, no other change. Now you will have the difference dy by dx, the differential value. Now think about this for a moment. In earlier equation, when I had 3x plus 2, your dy by dx was equal to 3. Now, can you tell me the differential value that I'm calculating? Where is my differential value dependent on the input x? Is it dependent in this form or is it dependent in this form? It depends when my equation is in squared form, right? Because in squared form, I will get my independent variable, right? Also play a role in the differential. Is that okay with everyone? Those who do not understand differential, I'm okay if you do not understand it. I'm okay with that part. It is critical for me. You will get to know about this when someone will teach you about gradient descent mechanism. I'm not going to talk about gradient descent in detail right now, but give you slight amount of idea. That is my ultimate objective. In order to find a line, that means I want to find a line which is y is equal to mx plus c. Good. Simple understand. I'm putting that as y hat. That is my prediction line. Great. Now, if I take that particular y hat, then for that particular y hat value, I will have an MSE value, mean squared error value, right? Can I put that as sigma y minus y hat the whole square by n? Is that okay? That is the average error that I'm going to get up. Good. But this line may or may not be an optimal line. I might have another line which is better than this line, correct? I might have a line which is better than this line. Let us take up another line. Let's say this line. Do we believe, first of all, that this line might throw up a different error? Different amount of average MSE value. Right? What I would have to identify whether this MSE value for this line is lesser than the previous one or not. Is it low or not? If it is low, then I will change my solution from the random solution M and C to that new slope and new intercept, correct? That is what I want to do. Now think about it. There are two important things I want to bring up. In the equation of that line, what does M controls and what does C controls? The M controls the vertical movement of the line. That means not M, but the C. The C controls the vertical. Suppose this green line, I can keep on moving that line like this, up and down. Does the slope change? No. The slope remains consistent on that line. The only thing that changes is the angle. The intercept value, right? Where it is cutting the y-axis, that changes. But the inclination remains the same. So I can have M constant, change in the C values. One change, good. Second change I can have is, which I cannot show it up here, but the M, if I keep this thing constant, I can have multiple lines passing through the same intercept where the slope is going to be different, right? I can have either M changing, C constant, or C changing, M constant. Make sense? Okay. Now, can you tell me how does the equation of square term looks like? So if you talk about equation or a quadratic equation, any quadratic equation, its picturization will look something like this. Isn't it? And a random value of C. Initially, I chose up a random value for M and C there. Sensible? See team, I'm going a little too deep. If you guys do not want me to go that deep, I'm okay with that part. But I can tell you, once you understand it, there is nothing will be left behind. So we started with a random value of M and C at the beginning, right? So let us assume that this is the curve representing the mean squared error relation. Now I'm going to write that equation again. Y is equal to, or my error, let's assume that is represented by letter J, is equal to, and I'm taking the total error equation, not the average. Good. Sigma y of I minus, can I put that as mx plus c, the whole square? Can I put it that way? I have replaced y hat with mx plus c, the equation of the line. Good. Now, because of this, at a particular random value of m and the random value of c, good, I will get some error, total sum error. Make sense? Let's put that up as a point on this curve somewhere. That will be a point somewhere here, let's say. Good. Now, if this curve represents the equation of my error, then your objective will be to reach out at this level. This is your minimum error, isn't it? In the error term, which thing I can vary? I have a fixed value of x, which is my input, and I have a fixed value of y, which is my output. So can I change them? No. What I can play around with is the slope and the intercept. Acceptable? Now, in order to make that play around with that slope and intercept value, which we started randomly at, what I will do here is I will take a partial differential. Now, many of you may not understand it, but I'll take a partial differential of my error term dj by df. I will differentiate on one dependent term, which is m, and I'll also take a partial differential with respect to c. Since it's a squared equation, I will have terms which are independent and dependent of both m and c. Agreed? By this, I will be able to find out a equation, a value of m and c, such that I have made some minor changes to the value of m and c, so that it reaches out to some point lower. See, I'm not putting up the exact details. How does it reach out there? But try to understand what I'm trying to convey. Let's say it reach out here. Yeah. So it will jump from this error to this error. Then from here to here. Then from here to here. Then from here to here. And maybe with small minor changes, I might reach out up to this point. So there is a lot of differential calculus involved into that. I will, and this mechanism that I've just shown up in this picture is called as a gradient descent mechanism or gradient descent approach, right? This is typically followed in order to minimize the error. Now, objective is, what is my objective? My objective is to find the minimization of this function. I want to minimize this. For the purpose of minimization, I need to take the partial differential of this equation. That's it. Partial differential. Why partial differential? Because I have two dependent variables, m and c. I want to vary both of them. Is that making sense to you? I will eventually reach out to a point where I will be able to find out the value of m, the slope, and the intercept c, such that I have the minimum amount of error. Are we good? And by this, we will be going to get up our line, which is my prediction line containing the minimum amount of error. Good. That is linear regression. Questions? All right. Now I'm going to put across that in a slightly different manner, and I'm going to put it down, or I'm going to change up some technical terms for you. Till now, what we have been doing is that I was looking to find the equation of a line y hat, which is represented as mx plus c. Good. Where I am finding, or I'm predicting that on the basis of that I have an input column x and a target column y given, and based upon the input of these two, I am predicting that this is my output. Is that correct? Where m defines the slope of the best fit line and c defines the intercept of the best fit line. Now I'm going to write this equation of line in a different manner. What I will write it down as y is equal to, or y hat is equal to beta naught plus beta 1 x. Good. That's just a simple nomenclature change and the terminology change. I have been calling this m as the slope of that line and this as the intercept. I can still use the word slope and intercept. It's quite understandable in the fraternity. But when you get into interviews or professional way, these have a different terms, right? This term, which is associated, which is a multiplier of m of my independent variable x, I call that as the coefficient of regression. We call it as coefficient of regression for variable x. Good. And the term beta naught is still called as intercept. There is no change into that. Good. I have not made any changes. Just m is changing now to beta 1 and c is now changing to beta naught. Rest of the equation, rest of the concept, everything is same. No changes. Just the representation of the equation changes slightly. Now we'll bring out the simple linear regression into two parts. The linear regression is divided into two parts. One is called as a simple linear regression and the other one is called as a multiple linear regression. Good. What is the difference? Whatever example that I've shown you or made you understand till now is an example of simple linear regression. What is simple linear regression? When I have one input feature, there is one input feature and one target variable, right? So my prediction equation is going to look like y hat is equal to beta naught plus beta 1 x. Please remember, beta 1 is nothing but the slope of the line which it makes with this particular input feature. Good. Now, what if I have a data like this? I have a column x1, column x2, column xn, and I have a target variable y. So my prediction will look like y is equal to, y hat is equal to beta naught plus beta 1 x1 plus beta 2 x2 up to plus beta n xn. If that does not sound correct, let me just put it across. Let me put across with two input variables as an example. That's something that I can show pictorially. Right? Suppose I have two input variables. This is your input feature x1. This is your input feature x2. And this is my target variable y. Good. Now think of my prediction line. My prediction line is a straight line like this. Now, this is 2D screen, so not imaginable. But if you have a pen or something handy with you, try to put that pen on the center of that screen or somewhere. Think of something protruding out of your screen. Right? That particular thing will make a different angle with this axis and will have a different angle with this axis, correct? Or it will have an angle with x1, it will have another angle with x2. They may be same, they may not be different, whatever it may be. Yes or no? So the slope of that line with respect to x1 is something different. The slope of that line with respect to different feature x2 is different. So I represent the slope with x1 as beta 1. the slope with x2, I'll represent that as beta 2. Or with, if I have, hypothetically present n different columns, for each different feature, it will have a different slope. I will not now use the word slope. I will use the word coefficient of regression. What essentially the coefficient of regression represents, I will talk about that too when I will explain R squared. When I'll explain you R squared, I'll tell you what is the relevance in terms. Why we are not using the word slope and using the word coefficient of regression. What exactly it brings it? It brings in a lot of things. Just a quick question to you. Right, so that looks fine to me so far. So if I have a single input column, I will say that as a simple linear regression. If I have multiple input columns, I will say that as a multiple linear regression. Questions? Ten. Okay. What I'm going to do here is before the break, I will just import that data set, import libraries onto my machine, and then import that data set and just look at the head values, just for basic information about the data, nothing much. Before I have to build up a new concept about train test split. So before that, up to that point, not too far off. So very quickly import the libraries. Import pandas as PD. Expected theme that you will be doing along with me, import NumPy as NP. Import the Matplotlib .pyplot as PLT. Import Cbon. I don't prefer that way. If you want me to do it that way, I'll do it, no problems. But what I generally prefer is people typing the codes on their own. Take your time, type it up. Time is not a constraint. Done. Let's read the data frame. Let's name that as df is equal to I have that data frame in the same drive. I'm using a local machine, read_csv. It's by the name tvmarketing.csv. Done. df.heads First, I have two simple columns. I have a TV column and a sales column. Good. Then I would like to have a df.info, quick look. So two columns, I have range index of 200 entities. Both are numerical, 200 non-null, so no missing values, nothing like that. Good. Some observations, I'm not putting those things into the picture. Good. Next objective that we have to do is to train and test the model. So before the break, we started off with one of the data sets called as the TV marketing CSV file, which contains two columns. One is the TV column, other one is the sales column, right? And my objective here is to predict the value of sales based upon the value of TV. Now, the number of TV, the value that you see for TV is some marketing cost, right? Some marketing cost of the televisions, and the sales values are reflecting the amount of sales that is happening. Good. So if I put about 230.1 marketing cost, the sales value is 22.1. If I put up 44.5, the sales value is 10.4. Essentially, what we're trying to find out the relationship between TV and sales, and what is that relation? Is that okay? Okay. Now, let's build up a concept, and that is to train test the model. What happens is that we have a finite set of data being given to us, right? In this particular example, I have two columns, right? This, I have a column of TV and I have a column of sales, right? Or in general, I will put up, I have an input column given and I have an output variable. And I'm representing that with the uppercase letter X and a small letter Y. Why I'm putting up the input as uppercase is because I may have a single column, I may have a combination of columns, right? Multiple number of columns can also be possible. So in general, we represent the set of independent features or all the independent feature columns as uppercase X, and the target variable is usually represented with small letter Y while doing, the nomenclature and representation. Now, what is my objective? My objective is to create a model. A model means I need to find out that relationship. So my objective is to find that y hat is equal to beta naught plus beta 1 x in general. Good. That is my objective. Now, in order to achieve that objective, let us suppose I find out that objective, I create up that equation by the given data. But I also need to verify how good is that, right? Is it performing good or not? So what we do eventually is, first of all, I will separate my data into two parts, right? I'm going to separate these two, input and output, separately. I will create a separate set of input and a separate data for output. X and Y are segregated now. Good. After this, I am going to choose out some percentage of data points of X, and I'm going to divide X and Y both in some ratio. Usually that ratio lies between 70-30 to 80-20. That's a common practice. You can have any of the ratios. You can go 60-40, you can go 90-10, you can go 75-25. There is no hard rule onto that. But yeah, it is usually between 70 to 80% bigger chunk and 30 to 20% the smaller chunk. Now, what is the objective? I am going to randomly choose out certain set of rows. Let's say I defined 70-80 ratio, 70-30 ratio. So out of total number of rows that I have, randomly select 70% on one side and remaining 30 on the other side. Good. And the same set of rows corresponding y values 70% on one side and corresponding y values on this side. So essentially, if I think about it, I have divided my data into four different sections now. Right? The major portion that I have, that is 70% portion usually, right? I call that as a train portion, right? I call that as a train portion. And the one that I've used here is a test portion. The very obvious question that arises is, why do we have to do this? Okay, so let us bring some real world perspective. Good. My objective here is to take a machine M, give it some data which is consisting of my input values and my output values. Based upon the understanding of machine of this input data, my machine is going to establish a relationship and create my model. Y hat is equal to some relation. Good. How it will find it? Based upon some algos. In our case, it is linear regression. Good. Is that okay? Now, if I test this particular model or this particular relation that we have identified on the already used inputs, right? Whatever the already used inputs are, which my machine has already seen, if I give those inputs, it is more likely that it is going to give me quite matching outputs because it has already seen that thing. Right? What do I want it? That I should be able to supply some inputs, but my machine has not seen those inputs before in the past, so that I can testify how is that model performing on unseen data in order to judge or evaluate the model's performance. Does that make sense? Let us consider one more example, seeing no confirmation coming through. Let us imagine that you are a model. You are a model. Right? Your objective is to learn. Let's say I am your guide. Now I have a pool of 10 questions. I have a pool where I have 10 questions and their corresponding answers. 1, 2, 3, 4, 5, 6, 7, 10. Okay, I have 10 questions and their corresponding. This is what I know. I already have it. Now what I will do here is, out of those 10 questions, I will supply you 7 questions and their corresponding 7 answers. I'll tell you both. I'll give you those 7 questions and 7 answers. Good. What you will do, you will learn from those 7 questions and 7 answers and make an understanding about the questions and answers. Agreed? So by that, I can conclude that you have learned something based upon the inputs that I gave, the 7 questions and 7 answers. Now, so that is your learned thing. Now, but once you have done that learning, I still have a bank of 3 questions and their corresponding 3 answers, right? Now what I'll do is I will only supply you those 3 questions and ask you to give answers based upon the learning that you acquired from those 7 questions. Does that make sense? So I will have certain answers. So I will have 3 predicted answers from you. Objective, I am dividing my set of original 10 questions into 2 parts. One of the part is I am using to train you or give you for learning, and the second part I am using for testing. Is that good? Testing your knowledge. So the division of my data for the purpose of evaluation of the model is what we call as a train test split. Good. So shall we do it? Let's do it. So first of all, what do I need to do? I need to divide my input features separate and target variables separate. So I have a data set. So let's separate or segregate the input features and the target variable. So here I can write down this is equal to in my data frame df dot iloc. I am going to select all rows, comma, all columns except the last one. And y is equal to my df dot iloc, all rows, comma, just the last column. Good. Done. I will have x now as the data frame and y as a series. Now let's perform the train test split. Now you don't have to do that manually, team, because we want to put up some randomization. So I will not do it manually. I'll use for the first time, take a help of a library, another new library. And that's by the name scikit-learn. So is a technique in machine learning, evaluate the model for dividing the data into two parts, a training set and a testing set. The model is trained on the training set and learning the patterns and parameters, and then evaluate and test it how well it generalized to the unseen data. Since scikit-learn in itself is a huge library, and I'm going to use selective things from it. So I will not import the entire scikit-learn module. I will import the very basic functionalities and classes wherever, whatever is required from scikit-learn, right? So as of now, my objective is to perform a train test split. It's a function available in scikit-learn model selection module, submodule. I'll take that up. So from scikit-learn, this is sklearn dot model underscore selection. You may not, think that, okay, these are certain things. How would I recall those things? But over the period of time with practice, you will remember those things. What is the purpose of doing train test split? It is an activity that allows me to help evaluate the model. Why I would like to evaluate the model? Because I want to select a model, I want to choose a model. So that is why it is put into the model selection submodule. I'm going to import train underscore test underscore split. That's the name of the function. Great. Now this is the beautiful function, right? What does it do is, it is a very basic syntax. It creates a NumPy array, right? And it can split, any sparse matrix, or you can say a data frame, right, into a randomized order. How will it do it? Listen to that very carefully. I will write down the function name first. Train underscore test underscore split. I want to split my x. When my x gets splitted, it creates two sections. One is the x training section, and the second one is x testing section. Good. Correspondingly, the way I am splitting the input x, I also want the same split strategy to be applied on y2. So I'll put up y. Next term is y. And when y is getting splitted up, it will show me y underscore train and y underscore test. Two things will come out from y. Good. Then I need to tell it that how much portion do I want to be given for testing, and how much portion do I want to take it up for training, right? So I can use either a train size or I can use a test size. So what percentage of my total data I want to use for training, and what percentage I want to use for testing. So usual term is we tell the test size, remaining becomes my train size. So test size, I am taking up 0.3. I want to take up 30% as training data or testing data, and remaining 70% as testing data. Oh, sorry, training data, my bad. Last property, very important, is random state. Now, what do I have now is, I have 4 different sections. I have got my data divided into 2 parts. I have this input X, this is target Y. I've got my X train portion, that is for training. Corresponding target variable values is Y train. And I have got X test data. Now, what do I need to do? I need to supply this to my untrained model, right? So that it can train itself. Sensible? Once it gets trained, I will look its evaluation on this data. So let us now, since the data is now ready, let us now evaluate. Let us now train the model on trained data sets. When I say trained data set, that means I have input data and output data both. So in order to do this, I need that raw model or blank model, right? So scikit-learn for every type of model has a submodule available. Since I am going to talk about a model which establishes a linear relationship, so it's a linear model that I'm going to create up. All the linear models are available in a particular submodule of scikit-learn called as linear model. So I am going to import linear regression class from scikit-learn linear model module. So import linear regression class linear model module. Right. Now, an instance of this linear regression class will act as my model. So from sklearn dot linear model, And it's not the only one model in linear model. There are other linear models as well. So this is the first one. I am going to import linear regression. Good. Once I've done that, I am going to create an instance of this linear regression class. Create an instance of linear regression. To create untrained model. Let's name the model name as linreg. I'm naming that as linreg is equal to linear regression. That's how you create an object of a class. Class name followed by a pair of parentheses to call its constructor. Done. Great. Now I have got a blank model, an untrained model. Just check it out. I want all of you to use that linreg, paste it up and execute. Some of you might be getting this kind of box, an orange colored. Anybody getting this? Collab people may not have exact thing, but should have something. Now I will hover around my mouse and I can see there is a question mark on this. That is documentation for linear regression. And then there is an iota sign or I sign. That's information. Let's hover it on it. What does it say? Not fitted. Not fitted means what? A not fitted means that this particular model has not yet seen any data. When a model gets fit, a model is fitted, that means that model has seen the data and has learned from that data. Is that okay? So what is my next objective? Next objective is to get this untrained model the training, or I need to fit the model. Let us now fit the model or essentially make model learn from training data. So how will I do it? I will ask my linreg dot fit function. So essentially all the model classes that we have, right? Whichever class that you will think of in scikit-learn, each of the model class has a function called as fit, a method called as fit, which is used to train the model. It is defined in that way. So, and I'll need to expose what? The data. So I will tell what is my training input and corresponding output, X train and Y train. Good. What is now going to happen? This linreg object is going to look at this train data from training data, whatever it has, and based upon that training data, it is going to find out the MSE value for a random M and random slope and random this, and then try to minimize that MSE function to get to a value of M and C so that it finds out the optimal value of M or C. Good. You don't have to do that manually. Model will do it for you. Let's execute this. I now see a blue box. Instead of the orange one, I see a blue box. And when I hover around my mouse onto that I sign, it says fitted. When it says fitted, that means it has seen the data. Are we good? If it is fitted, that means it has identified the slope and the intercept, correct? It has identified the slope of and the intercept values. So let's try to look at this. Let's print the coefficient of regression. Is. Why I'm writing the word is because I only have one variable. So I can put that down directly. That is linrag, that is my model, dot coef underscore. Now that's a predefined class variable, a class attribute, which captures the coefficient of regression for all input features. So coef underscore. And in a similar fashion, I have another class variable, which I can say intercept is. There is intercept. Can you check that, team? I have got the coefficient of regression and the intercept value. Now on this basis, can I write down? I've got this thing now. So I have got my beta 1, right? This is my coefficient. I have got my beta naught. So can I write down predicted sales is equal to the beta naught 7.23 something, right? Plus my beta 1, that is 0.04 times PV. That's my prediction. Isn't it? Or I can say my predicted sales is equal to this number multiplied with, plus this number multiplied with the value of TV, actual value of TV. Do we agree? Straight line equation? Yes, no, maybe. I am randomly selecting this one, point number 3. So my value of TV is 151 and my model predicted the actual value was 18.5. Good. Let's keep that into picture over there. So if I go by this equation, I will replace the TV value with this. So my model predicted the value is 14.27, this number. For the given data 151.5, it has predicted 14.27, whereas the actual value was 18.5. So can I find out the error? Yes, my error is 18.5 minus, you don't have to do this at all. Just wanted to make a picture clear for you. 4.22. That's the amount of error that is happening on that one particular data point. Is it? Is that acceptable? Yes, no, maybe. Let us predict from the trained model for training data, training inputs, and the test inputs. I'll tell you the reason why we are taking both. Good. So let's make that as y predicted values for training data. Good. How will I do it? Just like we have the fit function for every model, we have another function for every model, which is called as another method, which is we call it as the predict function. There are two more, transform and resample. We'll discuss transform and resample in upcoming time. Good. So what I'm going to use is, I will ask now, linreg is a trained model. Only a trained model will be able to use predict. I cannot use predict on an untrained model. Good. So linreg, I'm asking linreg to do what? Do predictions, predict for what? My training inputs. So x train, that's my training input. Similar fashion, I will ask it to predict on the test set too. Y train, Y predicted for the test data, and I will just ask it to pass it the test information now. It is going to, no, my bad, spelling mistake. Done the predictions. Good. So far, hopefully. The question arises, is that good? Now, I will not put the evaluation part right in front of you right away, but let's have a pictorial representation of this. Shall we? Let us visualize the predictions on train and test data. So I'm going to create up a graph, plt.scatterplot. I will take x underscore train, comma x underscore, y underscore train. So that is my input data. Let's put up a color value is equal to a green color. Good. Onto that, I am going to put up, do you want to put up a line or you want to put up a dots? The predictions. Predictions is dot or prediction is line. Choice is yours. Essentially, what I'm trying to do here is, I will plot my original data points like this dots. Now, what I'm asking is a line. Okay, great. I'll put up a line. The only difference is in the graph. I can put a plt.plot. If I use plot, it will plot a line. If I put up a scatter, it will plot up the dots. I will use the same input points for X train, but instead of plotting it against the Y train value, I will plot it against the Y train predicted values. Good. Let's put the color as red. Red looks good on green. I can now put plt dot title. Right. I can put up this linear regression model. TV sales. Train data. Plt dot x label. As I have TV on x-axis. Plt dot y label. I have sales on y-axis. What else? Nothing. Plt dot show. . 。 . 。 . 。 . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . .
So
Okay, that's the line. Just resizing the image so that I can show it up in one screen. CLT.figure. Good. What is your opinion? As per linear regression model, that's the best possible line. Or wouldn't it be better if I can find out this relationship like this? Or maybe going downwards like this. What do you reckon? Let's also have a look on to the test part 2. We have looked at the training data. Let's have a look on the test data too. How was it looking like on the test data? So I'll copy the same graph. I could have done it through function. Creating one function, passing on the data. But I actually wanted to split it out. So instead of xtrain, I will change data to xtest, corresponding xtest value, ytest values. Here again, xtest and y predicted test data. And here also I'll put up test data. Good, that looks fine to me now. All test points plotted and corresponding line also plotted up. See team, you might think that, okay, that line here and this line here does not look parallel to each other, may not look. Why? Because the scale on y-axis is different. On y-axis here, the scale is 0, 5, there's a gap of 2.5. Here the scale is 5, 10, 15, 25. So slightly different the orientation might look like, but they're essentially same. This is going to cut down the y-axis at somewhere around 7.2, right? So does that. Good. In order to judge this model, we had a data, we trained a model, a linear regression model, we trained it on training data, we found out the predictions on the training data, we found out its prediction on the testing data too. Good. But let's try to understand what meaning does it make to me. It does not make any sense to me up until I can verify or justify whether it is good or bad. Or should I look at some different thing? Or should I stick to the same thing? I do not have a choice. I may have certain situations where I might not get a choice. Right? So in order to do this, I will not talk about too many things, but let's have a look at 4 different metrics, right? Rather 2 metrics. I will, since I have explained you what is mean squared error, so I understand you guys know what is mean squared error, but there is another metric that I'll bring into the picture, which is called as an R squared value or R2 score. But as of now, you can assume that R2 score is talking about accuracy in percentage. How much accurate my model is. Now, let me remind and give you a disclaimer. R2 score is not the accuracy of the linear regression or any regression model, right? because MSE, R squared, MAE are your go-to metric to understand any regression model, be it linear regression or any other model. We will always look at these three parameters. But R2 score, generally people get confused that it is the accuracy of regression model. No, it is not the accuracy. But as of now, since I have not taught you about it, you can assume that for tonight, let's calculate, or let's populate the performance metric or the evaluation metrics for a regression on the trained model. Regression for the trained model. And how will I do that? Again, since these are some performance metrics, so these are available again in scikit-learn under a submodule called as metrics. So from sklearn dot metrics, I am going to import mean underscore squared underscore. We can calculate them manually, but no point. We have already the functions available. R2 score. We'll look into these two right now. MAE, MSE, I'll bring on to a different data. The RMSE and separate things. Good. We already have the training predictions available. We have the testing predictions available. So I can directly calculate, let's say, mean squared error that my model made on training data is equal to mean underscore squared underscore error when I had y train. This is my actual data, and y underscore train, what was the name that I chose? Oh, it's y predicted train. So what I'm giving it, the actual values and the predicted values. These are the only two things that I require, isn't it, to calculate MSE? Because what was MSE? Actual minus predicted, the whole square divided by n. And you need to put up a summation over there. That's it. That's your MSE, mean squared error. So I will supply actual value, predicted value, mean squared function. It will do my job. In a similar fashion, I can calculate the MSE value for test data, y test, and y predicted for test. In a similar fashion, I can also calculate the R2 scores as well. So I will change the term here, R2 train and R2 test. Change of the function from mean squared error to R2 underscore score, and so does here. I've got the calculations done. Let's print them quickly and wind it up for the day. Print. I'm using short notation, but that we find MSE for trained data is MSE trained. So controlling the decimal point representation over there. MSE test data is MSE test. Then I have R2 train is R squared value for train, and I have R2 test. I can put up here R2 test value. Now, what do I want to leave you with is to think. This is what I want you to do with. Good. If I look at this results and I assume that R2 square or R squared is my accuracy, right? Now, if you think that my model has already seen the training data, isn't it? It has already seen the training data. Acceptable? It is making more amount of error on training as compared to testing. Average error on training is more than testing. Or in a similar fashion, you can see the percentage. If you think that is an accuracy, I have a lesser percentage here on training as compared to testing, correct? But when you give him some separate 3 questions, which is he has not seen before, it does a better job than this. Because whatever he has learned is not able to do that job, not able to replicate that correctly, but on something unlearned. So can I say that is an under-trained model? There can be thousands of reasons behind it. I will not talk about the reasons right now. Good. Why? Because my model is not able to replicate or is not performing better on the things that it has already seen, which I expect. There things that I already, questions which I've already seen, problems that I've already seen. I know the answers already. I am not able to replicate those answers itself. If I'm not able to do them better, then how can I expect that I'll do it better on the unseen data? It might do it for some cases, but not always. Good. Did I make any sense to you? I talked about a lot. Okay. I am expecting that I would be able to reach out to at least performance evaluation matrix because we have a polynomial regression in between as well, right? So overfitting and underfitting followed by polynomial regression and then the performance evaluation matrix. Because since we have done almost 50% of those, I only need to explain R squared, which we can do quickly. It's your time. Right? Please take a pause on that. We'll discuss. It is going to come up today. Just a pause on that. Okay. Team, as the word suggests, underfitting and overfitting. What is the purpose behind it? Okay. Let us suppose, I guess all the males and females, gender wise, no discrimination. Both of us wear shirts. Can I say that? Gender wise. We would have certain females and males in the house. Both of can agree or disagree. Shirt, I can say, is a common kind of thing that either gender wears. Agreed? I am building a concept with those shirts. So I need some quick responses. So I got a response from Pragati, considering Pragati is a feminine gender, Parthin I'm considering as a male gender. I have one response at least from both the genders. Now, let us imagine a situation that this is you or me. And we got onto a garment stitcher, or you can say a tailor who stitches the garment. Good. Now, if I ask the tailor to stitch a shirt for me, Both males and females in the house will answer. Good. And the, the, the tailor or the garment stitcher, whatever name you want to put up, right, has given me a this kind of fit. These are my arms. And remember, this is me, not you. The blue line, just imagine that's the fitting of the shirt that he has given to me. Is it a too tight or is it too loose? Too tight for Solomon. A fit for Parthian. Three different people, three different opinions. A slim fit for Masood. I'm okay with slim fit. Okay. Now, what if today when I got that stitched up, now I was, empty stomach. Now, when I got the measurements done, I was empty stomach. Good. My tailor stitched that up at an empty stomach. Make sense? Now, when I'm full, will this shirt, which I am finding it completely fit, or let's say in some situations I went ill and I lost out on weight and I have become little more leaner. No, right? That is what we want to try with the underfitting and overfitting. What I want to establish is that when I create a model, the one meaning is that it performs good on trained data and performs good on test data too. But the performance difference on train and test, I am performing better on training data as compared to testing data. Was it good or was it bad as compared to test? As compared to test, Sangamesh, I can scroll back up and you can see the result. This was the information. You can look at the test and train information. If you do not know R2, I'm okay. Better, okay. My performance or my error on training is 11. My error on testing is 8. So testing error is lesser as compared to the training data error. So my model is not doing good on training as good as it was doing on testing. And what do I ultimately want to achieve is a right balance wherein, see, the ultimately what I want to achieve is, and why do I want to achieve it? Both things. I want to achieve is that when my model is learning from something, some data, it can show its performance on the learned data. Agreed? We can check that. Agreed, yes or no? I give you 7 questions. You learn from those 7 questions and their answers. Then I give you the same questions back. And you can answer those 7 questions. Correct? So can I judge your performance on those 7 questions which I've already given to you and their answers? Can I judge that? So performance on the data which is seen. One point, correct? Then there will be a performance which can again evaluate on the data which is not seen, because I have never shared you those answers. Sensible? So I will have a performance on seen data. I can have a performance on unseen data. If that is okay with everyone, can I get these performances? Let me put it across in a different manner. Maybe the Taylor example did not work out. I'll put it up in a different manner for you now. Now, what I'm trying to talk about an underfitting and overfitting concept, right? Now, suppose there is a model, right? There is a model. The model, what is the objective of this model? What we have seen is that the objective of the model is to learn something. What it is going to learn? Let me ask this question. This should be answered. In linear regression, what is the learning that my model is doing? What is patterns in the data? No, Pragati. In linear regression, no, not in the input and output. Parthi. What is my model learning in linear regression? The linear regression model, what does it learn? Next possible, no, Masood. One input, no. I'm going to scroll back up slightly. Not if you recall it correctly, when my model was learned, this is the learning phase, right? I make model learn from the training data. And immediately after that, what did I show you? Two things, the coefficient of regression and the intercept, the slope and the intercept. Did I show that? That's why model learned, correct? Coefficient of regression and intercept, good. That's the learning part. Now, when it learns something, right, it is possible that it might learn too well. Now, there is a common example that I quote up. So I'll ask a very generic question. People from outside India, anybody from outside India in the house? Information is not performing good on the shown information or the training data, as well as the performance on the testing data is also not good. So whatever I've seen, I'm not doing good on that. Whatever I've not seen, I'm not going to do good on that either. That is an underfit. Make sense? Why is that going to happen? because I am unable to learn. I am too simple. I cannot capture the concept behind it. If that makes any sense to you. I am the dumbest guy in the house, right? You tell me 2 plus 2 is equal to 4, but I never understand it. If you ask me next time 2 plus 2, I might put up 22. Because I never understood the concept that there is a number line and you need to move around plus and minus. Can you give that a quick read, team? Overfitting and underfitting. I want to convey this. I have not yet talked about what is the bias variance trade-off. I will give that a read, but as of now, what I want you to understand is the overfitting and underfitting. So just give that a quick read up to this point. My objective, Parthin, is that whenever we are trying to develop a model might be doing very good on the training data and not doing as good on the testing data. That is an overfit for me. A model might not be doing good on the training data as well as on testing data. That is an underfit. I need a model which is doing good on training as well as testing. That is the objective of trying to talk about all the new science that I've talked about so far. What I want is a model which is performing good on both training and testing information. That's not yet done. Because we need to do that through codes. Right? I cannot just make it, randomly selecting that up. I'll give you through coding and I'll tell you a general perception as well, a generic idea. Overfitting and underfitting. Great. Now, I am going to bring in two terms for you. The terms are called as bias and variance. If I go by the textbook definition, right? As per the textbook definition, bias is an error that is caused because my model is simple. That means it is not able to learn things, right? It is not able to learn things. It's very simple model, right? It is not able to get the information correctly, not able to capture things correctly. The variance is the error that is coming because my model is too complex. It is doing an overlearning. That means I'm learning too many things because of which I'm getting error, right? So variance is an error that happens because of overlearning, and bias is an error that happens because of underlearning. Does that make sense? So variance is something that is going to come across with overfitting, and bias is something error which comes going to come across with underfitting. That's the textbook definition. You will find that into notes. Are we good? Now, let us understand the practicality version, right? What you need to understand in terms of the bias and variance, right? Now, I am going to put across some set of data in front of you. Okay, there are two sets of data. Let me name that as D1 and D2. Good. Now, very simple question. What is your opinion about the variance for D1 and D2? Which one has a high variance? So variance specifically talks about the spread of the data around the mean or disconnect, according to my knowledge. Partly. Why do you say D2 is a high variance? I'm okay to look at your perspective too, but let me know. Essentially, what I consider is that a D1 on my screen, fitting is not a problem. I have not talked about the fitting part so far, Parthin. What I've talked about is the variance, only just the variance. Among those. Let's now think about a prediction line. Suppose I have a line that I have predicted for this data, my linear regression line like this and like this. Good? In both cases. Now, I'm going to bring up the second term, we call it as bias. Bias is my difference between the actual value and the predicted value. Bias is nothing but my difference between the actual value and my predicted value. Now, can you tell me where do I have a bias higher and where can I have a bias lower? I have two sets, D1 and D2. Sorry, a high bias here and I have a low bias here. Now, out of these two lines, right, these two prediction lines, which one do you think is a better prediction? The only thing that changed between D1 and D2 was the variance. In D1, I had a high variance and here I had a low variance, because of which the line that was predicting, I had a high bias here and low bias here. Does that make sense? What is the regulating factor over there? It is the variance, correct? That has predicted a line like this. First question, is it possible for both D1 and D2? I still have high variance and low variance. So the variance still the consistent. What has changed here is the bias term. Isn't it? I still have a high bias over here, and here I can again say that we have a high bias. Right? Now, what does this mean when I have a low variance and a high bias? When I have a low variance and a high bias, what does it mean? It means that, think about it for a short while. I have a very clustered data and I am predicting something out of the box, right? All my people are living in North America. I am predicting South America. All my people in North America, low variance, correct? I am predicting South America, high bias. Does that make sense? So I have many people from India. Let's say all my cluster of the learners are from northern India, and I'm predicting that people are from southern India. What I'm predicting is it is from south. Am I learning good? The answer is no, I'm not learning good. Why? My majority of the data is in the current scenario when my variance is low, still I get a very high bias. That means I have an underfit model. My data is very clustered, still I am getting too much error. I have a data which is very closely packed up, but I am putting up an answer which is way different. That means I am making a mistake. I am not able to learn the data correctly. An underfit situation. Good. There can be one more situation where I have a high bias, or sorry, high variance, but a low bias. How can that happen? Very low bias. How can that happen? What if, let's suppose I am predicting a line. It is not a straight line, but I am predicting my result like this. Now, can you tell me the amount of difference or amount of error in this situation? It's a complex thing, Manjunath. Agreed. Does not make a difference for me. But think about the difference between the actual and the amount of error, the bias term, just only the bias term. The bias is going to be low, yes or no? But my variance is high. So this is an overfit situation. Because if I have another point here, I do not know whether this line is going to come down here or is going to go back up on that side, because this relation is very complex, isn't it? That's an overfit. That is overfitting. Right? So when you have a high variance and low bias, that attracts overfitting. When you have a low variance and a high bias, low variance and high, that attracts underfitting. So what essentially we need to do is we need to find out a balance between the variance and the bias, right? I have not yet reached to that point, Kiran, but yes, the answer to yes, your question is yes. I have not yet reached to that point where I'm going to discuss the performance matrix. Kiran, I will come across with that today itself. But if you ask me that question right now, the answer is yes. Yes, RMSE does help in understanding how good or bad my model is. So essentially, if I talk about, and if I have to represent this thing, right, I can represent the relationship between the bias and the variance. If this is your bias and this is your variance, good. So your variance curve will go something like this, and your bias curve will go something like this, right? So if your variance decreases, right, the bias might increase. So at some point, somewhere, you will have an optimal value of variance and optimal value of bias. I might not require a minimum variance. I might not require a minimum bias. A balance is, or in simple terms, if I have to talk about in a very simple language, a balance is when, and I'm able to replicate similar on testing data, I am good. I say that I am 60% accurate whenever you ask it. You give me a data that I have seen, you give me a data that I have not seen. I am saying that I am 60% accurate. You will trust me my 60% accuracy, right? For example, good, might have seen that, right? Now, if now you're connecting with the live session and now you see that whether I should be rated 3, should be 5, should be 4, you know it well. But am I doing the same thing which is there available on the unseen user and not seen user? If I'm able to replicate it the same way on seen data, then my known learners make sense. So expectation is important, and that is what bias variance trade-off talks about. What I am expecting from the model, is my model giving me the similar kind of things on unseen data? That means my model is able to generalize on unseen data the way it is showing up for the seen data. Does that make some kind of understanding, team? Again, team, I'm telling you, I'm taking my time. I'm okay with that. because I know what I have to cover and how will I cover. I'm trying to build up a very strong foundation, very, very strong foundation, so that I can, rush through at the end. But questions, please, quickly. Again, please. Okay. In a very simple norm, if I have to talk about, if you have a low bias and a high variance, right? I will say the data is an overfit. The model that I have given is an overfit. If I have a high bias and I have a low variance, that's an underfit, right? And if that happens, so that means I need to strike a balance between bias and variance. The balance between bias and variance will decide the trade-off between them. So I need to find out a particular value. I need to look at a value of bias and a variance in such a manner so that my model has equivalent performance on the data or the training data or seen data and unseen data or the test data. So my performance as a model on the training data and testing data should not have a huge gap. What is that huge? That is going to come in practical. Good. Right. Now, how do I quantify this part? I want you guys to give that a quick read. Done? Hope so done. Let's move on. Now, what I'm going to do here is practically going to check whether my model is an overfit or an underfit model. Can we do this? Check for overfitting and underfitting. Now, there are two criterions. As I told you, the performance on training data and the performance on testing data is the go-to thing. I have calculated MSE train, the MSE, the mean squared error, and R squared values. So I can use either of them in order to judge the overfitting or the underfitting of the model. Good. So how do I want to check it out? I'm expecting, team, that you guys have the same file with you. If not, let me know. Good. So how will I check it up? If my model's training error, listen to that very good. My model's training error is MSE underscore train. Is that correct? How much error it is making on the training data? If that is less than the error that it has made on testing data. So error that I'm making on the things that I've already seen is less than at this juncture. I am making less errors on the things that I've seen as compared to the things that I've not seen. Is it okay behavior or non-okay behavior? Okay, I guess I'm not audible. According to me, it's an expected behavior, right? Things that I've seen, I should be doing good on that as compared to things that I've not seen. Or my accuracy on the data that I've seen, so R2 train is greater than the R2 test. So either my error on the data that I've already seen is less as compared to the data that I've not seen, or my accuracy level on the data that I've seen is more as compared to the data that I've not seen. In both the situation, I am expecting an okay behavior, but there's a problem with this. The problem is that if that happens, there should not be too much difference, right? Let's say I am attaining an accuracy of 90% of the things that I've seen, and I'm attaining an accuracy of 60% of the things that I've not seen. So there's a huge difference, right? Think about it. Is it good or bad? I'm giving you two choices, good or bad. Okay. Let me tell it in this way. Pragati has given me her age at 19. Very simple question. That passes, so, and when I say 19, I'm 90% correct. Just an example. Good. Pragati has already given me a data that her age is 19 and I predicted 18.5. Good. Pragati is happy. Good on training data, known data. Basi has an actual age of, let's say, 20 and I predicted 65. 90% here, correct. But on unseen data, I am 60% correct. Now tell me, is it good or bad? But on unseen data, I'm not doing as good. Definitely not good, right? So I need to strike out how much difference between the training performance and the testing performance is acceptable to me. On the training data 90% of the time, and I'm doing 85% of the time good on testing data. Is it acceptable to me as a data scientist? It is my choice as an individual, as a data scientist, as an AI engineer. It's my choice. Whether I am okay with 90% accuracy on training set and 85% on testing set. That is completely upon me. If you talk about me, what is the regular practice in industry? There is no standard for it. A practice part I can tell you. Should we? Shall we? So what I'll check over there is if that situation prevails, my model is giving me less error on training, but more error on testing. Right? My error on training is less as compared to the error on testing. Then I can check a comparison. If the absolute difference between the R2 train and the R2 test, right? If that difference is greater than 10%, good. If it is more than 10%, I will say that model. Now, some people take it as 5%, some people take it as 8%, but maximum usually followed in industry is what 10%, right? So my error on training data is more than 10% high. That means I'm getting an accuracy of 90% on training and accuracy of 80% on testing. That's a gap of 10%. Is that acceptable? then I will say that is print the model may be overfitting to the training data. Good. Now again, I'm saying that this level 0.1 is not a standard. It's an industry practice. Industry practice and standard setup. There's no standard into this. Typically, no standard. You can manipulate it as per your choice. The more stricter you want to go it, it's your choice. I want perfect kind of model. You can go at 1% difference. What I've taken here is 10% difference. Good. If that does not happen, right? That means I have this situation. Okay, my training accuracy is more and testing accuracy is less. Yet the gap between them is less than 10%. That can happen, right? So that is my else position over there. Else. Model performs reasonably good. But check for slight overfitting. There might be small little bit of overfitting that might be happening. But kind of okay, acceptable to me. Good. That is within my acceptable limit. Okay, I'll say that okay, it's fine. Otherwise, I'll say it's an overfit. Otherwise, what can happen? The second situation that I put up is an elif condition for the both situations, but slight change. Elif, if my mean squared error on training data is more than testing data, and now I'm combining it, not the or situation, but an and situation. The R2 train error on training is less than the error on testing. Then I would say that model may be underfitting. It's an underfit model. Consider increasing model complexity. I have not talked about the complexity and simplicity of the model so far. I'll just give that an idea. Now, if either of the situation does not prevail, then I can have an else condition. Else model has a balance fit on both training and testing sets. Essentially, if you look at this, you would rarely reach out to this situation. On a real world data, a balance fit is a myth. That would be either slight overfitted or underfitted. At the most, what we can achieve is either a slight overfitting or an underfitting. That's the utmost. You will never be able to attain a balanced fit in real world situation. Anybody else got something else? I'll now bring the role of seed now to you guys. Good. I'll scroll back up on my screen. Same data, no changes. Here, in my train test split, I'm going to change my seed number. Let me make it 25. That's my lucky number. Good. I love this number 25. And I'm going to restart the process from here. Remember my last results, team? What did I change is only the seed number. Rest, I'm not changing anything. And now it says model performs reasonably good. I missed all the spelling. But check for slight overfitting. Did that change? Just because the change of the random state value. And there is a change in my values as well. If you look at my R squared values and performance matrix, the error on training is now lesser as compared to testing. And the accuracy on training is higher as compared to testing. The gap between train and test accuracy is less than 10%. Isn't it? It's approximately 8%. If I go back and change my threshold here to 0.05, that I want my model to be at least there's not more than 5% gap allowed. I am getting an overfitted model. Sensible? So this is a generic approach. You can always use this piece of code to check whether a model is overfitting or underfitting. The only thing that you need to remember is that you need to look at this criterion, whether I want or I am okay with a gap of 10%, I'm okay with a gap with a 20%, I'm okay with a gap of 5% between the training performance and the testing performance. Is that okay with all? I'm sorry. Now, polynomial regression essentially is nothing different. And I'll ask you a very simple question. What is the difference between a linear and a polynomial? A basic concept, basic question coming from the mathematics. What is a difference between linear and polynomial? So if I write down an equation, y is equal to mx plus c, where x is the unknown term. X is the unknown term. This is linear, right? It's a single line because the degree of my unknown variable is 1. The power of it is 1. If I write down y is equal to mx square plus c, the degree of unknown term is now 2. Quadratic equation, right? Or the degree might vary to 3, 4, 5, 6 up to n term. It can have any degree, right? But the problem is, the difference is, if the relationship I'm trying to identify is as mx plus c, right? That is going to be a very straight line. Good. If it becomes a square term, then I'm going to get a slide curved line. If it is a very complex thing, I might get something random. Does that make sense? I can have a question, parabola, hyperbola, whatever it may be. But do we agree on this? Depending upon the equation of the relationship, if I'm identifying the relationship in the nature of a straight line, then I will have a degree 1 equation. And if it is not a straight line, it is any kind of line which is not linear or non-linear. It is going to be a it's going to be a polynomial line, or line which is curved or a complex shape, or whatsoever you want to say it as, right? If that happens, that essentially means that we are trying to get up a relationship which is of polynomial nature. Do we agree? Eyes, nose, maybe. Do we agree? Somebody. I guess it is getting monotonic right now. Nobody is liking it. A straight line without a slope. I have taken input X. This is your output Y, target variable Y. A straight line without a slope. Slope means, that means my slope value is 0. Slope is equal to 0. Is that what you mean? Kiran Bhaskar? Great. Now, if slope is equal to 0, it means that the tan theta value is 0. When is the tan theta 0? When the angle between is 0. Tan 0 is 0. Tan 90 is undefined. Manjunath. It's actually undefined. It's divided by 0, right? So I can see a line where the angle is 0 is like this. This is your prediction line. Now at this point juncture, what do you think that? Does that prediction line, which has a slope 0, that means the value of m, x plus c, m is now 0. What is the relevance of x? Does x makes any impact the input? No, right? X does not make any impact. When my slope is 0, it means that the line is parallel to my x-axis. That essentially means input has no impact on the prediction, not at all. Or input has no role to play in defining the output. Make sense? When the slope of the line is 0. Is that sensible to you? Yeah, that means no relationship. In fact, I should not use the word relationship. I'm going to use a different word for this. The word is the explanation. How much is my target variable explained by the input variable? How much is X able to predict Y? Right? If the relationship between X and Y shows me a 0 degree or no slope at all, it means that X has no role or X has no impact in determination of Y. right? Whatever the value of x may be, y is still consistent, right? If you look at this graph, so what I'm going to start off now is the polynomial regression. Understand what is the concept behind polynomial regression, what exactly polynomial regression means, right? We'll build up the concept first and then I'll talk about it. How do we implement it? Now think about a linear regression problem. Great. Suppose you have a data, a very simple data. Suppose there is a very simple data. I have one input column x and a one target variable y. Good. That contains some data points. Good. Let's say the value of x is 1, 2, 3, 4, 5, and 6. And the value of y for the corresponding x is 1, 8, 27, 64, 125, and 216. Now, if I ask you by looking at data manually, what is the relationship? Can you define the relationship y as a function of x? Simple. Very simple thing. Now, let me ask you, can you define that relation in terms of a linear equation, a line? Can I represent that relation in terms of a line? Out of that, y is most important. What I can do here is I can perform some changes. What I can do is I can represent my x, the input feature, in polynomial terms. Or essentially what I'm trying to say is, can I not create up a data set like this, wherein I have the target variable, okay? This is just an example, okay? I have x value, that is 1, 2, 3, 4, and 5, and 6. Good. And I have the corresponding values 1, 8, 27, then I have 64, and then I have 125, and I have 216. Good. That's the given information to you. Now, from the given x, can I create in my data frame another column which is x to the power 0, another column with the x to the power 1, another column with the x to the power 2, another column with x to the power 3. Let's put up one more line here, x to the power 3. Make sense? Can I create it? That's the basic thing. Feature engineering, you might have studied before that. In my data frame, I am creating another column which is derived from the given column. If that is okay with everyone. So x to the power 0, I will have 1, 1, 1, 1, and so on. X to the power 1, I'll have 1, 2, 3, 4, 5, and 6. X to the power 2, I can have 1, 4, 9, 16, 25, and then whatever that number is, 36. X to the power 3, I'll have the requisite numbers. But if I try to establish a relationship now, can I say that y is equal to the prediction value? Y predicted is equal to 1 times the x raised to 3 column. Let's represent this column P3. I'm going to represent that column name as P3, right? So let's name as P3, x raised to P3, or 1 times a P3 column plus 0 times the column P2 plus 0 times the column P1 plus 0 times the column P0 plus some constant 0. Where P3 is x cube, P2 is x square, P1 is x raised to 1, P0 is x raised to 0, and constant I have something. Now, can it say that if I try to convert my input column x into multiple number of features, which are the polynomial terms of x, the input feature? Good. I've converted it into a polynomial form of my choice. I can go up to degree 5, degree 4, degree 2, degree 1, whatever I want. That is up to me. Good. And based upon that, it converts my input set of features into multiple number of entities. And then I try to establish a line, a straight line. Now, can I say that this is an equation of a straight line? Degree 1, right? And that is all what we are trying to do in polynomial regression. What we're doing here is, in polynomial regression, I am going to convert a column, a single column, into polynomial terms. So what I'm changing is the input terms so that I have the polynomial terms of my input data, and based upon that simple polynomial terms that I'm extracting, considering them as a linear part, I'm trying to establish a relationship of the polynomial terms with the target variable. Does that make sense? If that is okay. Right? What I believe is that instead of this straight line, if I represent that relation like a curved graph like this, that might be a better representation. What do you think? Might be. I'm not saying it is, but it might be. So I might want to depict a relation in terms of a nth degree polynomial instead of a linear equation. Make sense? And in order to achieve that, what I can do is I can create that equation. Let's imagine a simple example. Scroll down. I need to get a white space. A very simple example. Suppose a data that contains three numbers, 1, 2, and 3. And the target variable is 1, 4, and 9. Good. This is your input X and this is your input Y. Now, I can write Y is equal to X square. Right? Agreed, yes or no? But this is a quadratic equation, a polynomial equation, correct? This is a quadratic equation, an equation of degree 2, not a linear equation. But can I create that in a linear terms? The answer is yes. How? I can divide this X into two parts. I can say X is, let's say, Z1 and Z2, and I can write down Z1 as, and let's say Z3. I can write it down as Z1 as X to the power 0, so 1, 1, and 1. Z2 is X to the power 1, that's 1, 2, 3. Z3 is X to the power 2, that's 1, 4, and 9. And then I have Y. Now I have changed my data. The input now changed from X to Z1, Z2, Z3. And now I can reformulate the same thing as Y hat, or my predicted line, is equal to 1 times Z3 plus 0 times Z2 plus 0 times Z1. Isn't it? So my slope with respect to Z3 is 1. My slope with respect to Z2 is 0. The slope with respect to Z1 is 0. Does that make sense? But if I formulate this equation for any value, my predicted value Y hat is going to be 1. When X is 1, my Y hat is 1 based upon this. Right? Because I'm formulating changing X to Z1, Z2, and Z3. What is X to Z1? X raised to 0. What is X to Z2? X raised to 1. What is X to Z3? X raised to 2. So what I'm trying to do is I'm creating a polynomial term of my input variables so that I can establish a polynomial relationship between my target variable and my input variable. Does that make sense, team? Or essentially what I'm doing is a linear regression. I'm still trying to establish a straight line, but that is divided into parts. Right? So instead of drawing a line, I'm drawing a line segment. Or I can say that I'm drawing a relationship between the independent variables X and the dependent variable Y as an nth degree polynomial. If that makes any sense to you guys. Are we good? So for the same data that we have worked before, putting up some theory notes, copy paste. Great. it's a subset of linear regression. What we have is a polynomial regression. The relation between the independent variable x and y is modeled as a real polynomial, a very special case of multiple linear regression. So what I'll do is I will add up some polynomial terms. That means if I have an input feature x, I will find out or I create a feature x raised to 0, x raised to 1, x raised to 3, x raised to 4, x raised to 5, up to whatever degree I want. That helps me understanding the relation, right? That is your polynomial. So polynomial regression, which talks about the curve or non-linear relationship, is a myth. It's actually a linear regression of polynomial input features. What I'm expecting is that the input features, if they have a polynomial relationship among themselves, I will get a curved line. Make sense? If not, let me know. The same data set that we have worked before, if you recall it back, I'll scroll it up. We have the data set right here. I read the data and I performed a train test split. So I have X train, X test, Y train, and Y test. So I'm going to use the same X train, X test, Y train, Y test. Are we good? So I'm going to using the same train test split data from previous example. Good. I'm going to use the same data. Now what I'm going to do is whatever the input features that I have, I'm going to convert them to polynomial terms, right? Let's perform feature engineering. To create polynomial terms for input features. Now, in this particular example, I only have one column, so I will have polynomial of one column only. Good. Number of polynomials depends upon us, right? So in order to do that, I do not have to do it manually. Scikit-learn has given me a class which I can use and create those things. That is coming from sklearn dot pre-processing, because that is my data preparation part. So dot pre-processing, I'm going to import a class called as polynomial features. Class named is polynomial features. Good. Now let's instantiate that class polynomial features, whatever you want it as. Let's name it as poly features. Is equal to this class polynomial features, and I will tell up to what degree I want to go with. Let's suppose I want to go with degree 4 or degree 5, let's for example. Now this degree term is up to me. I can choose up any degree level that I want. What does degree 5 means? Degree 5 means whatever input columns that I will provide to this object, it is going to convert those columns to the degree. Let's suppose if the column is x, it is going to convert it to x raised to 0, x raised to 1, x raised to 2, x raised to 3, x raised to 4, and x raised to 5. So when I say degree 5, it means I am going to create a column from degree 0 to degree 5 so that I can establish a relationship with y is equal to x raised to 0 plus x raised to 1 plus x raised to 2 and so on with some constants. Sensible? So that's my poly features. Now, as per my original data, right, I have x train and x test. So let's try to create up the training data for this particular model and testing data. So I will create x train data with polynomial. So poly is equal to, and I'll put up poly features. That's my object dot. Now, any kind of model or any kind of class, I have told you that you have a fit method that allows the data to be learned by the model. So if I can use here fit and I'll tell it x underscore train. So it is going to learn from the x train data that what kind of data that it has. Good. But I do not want to just learn. I want to modify this x train data. Right? So I can do it in 2 steps like this. I will first ask poly features to read this data and understand. Once that is done, I can ask it that you need to make up a different column, which is x underscore train or different data underscore poly is equal to the same thing, poly features dot transform. Now, what is the role of transform? The role of the transform is whatever the input that I'll give, apply the algorithm of this object and change the data which is given. So modify the data. That's the role of transform, right? And I can ask it to modify x underscore train. In a similar fashion, I can again ask it to modify the testing data, x test poly. Let's name that as x test poly, and I'll ask you to transform the x test data. Done. Now I have a choice with this that I can allow this fit and transform to combine together, right? The fit of the train and fit of the transform. At this both juncture, I'm using the same data. So I can alternatively use a statement which is like this, which is fit underscore transform. Now, what happens is that's a combination of both fit and transform together. So as I have a fit function, as I have a predict function in the algorithms, I have another function called as transform. The role of the transform function is that whatever input data that you give, I will modify it and send it back. Sensible? Hopefully, yes. So either you can use this statement or you can continue with these 3 statements. Both are same, not doing a difference. Good. Now, just to showcase, let's have a look at x train head value dot head. That's first 5 values. Let's look at first 2 values only. So I had 135.2 and 129.4. Good. Now let's look at x train poly. Now this is going to be an array, so I cannot show it directly, but let's look at x train poly :2 so that I can see the first 2 rows only. Now, if you look at the first value, let's look at the first value only, :1. So that's your first row of data. 135 That's my first value. 135 raised 0.2 raised to 0. What is the value? 135 to the power 0. What is the result? 1. Correct? 135 raised to 1. What is the result? Scientific notation 1.35 raised to 0. Raised to 02. So that's, you can multiply that to the 10 to the power 1 or 10 to the power 2. Sorry. That's 135.2. If you take it up as 135 raised to 2, that's here. 135.2 raised to 3, that's here. That's raised to 4 here and raised to 5 over there. So what essentially I have done is, from a data which was single column, I have a single value 135. I have created 1, 2, 3, 4, 5, 6 values which are of the nature. This is value raised to 0. This is value raised to 1, value raised to 2, value raised to 3, value raised to 4, and value raised to 5. Why value raised to 5? Because in my polynomial features, I have given degree 5. I make it degree 3 just for the convenience to understand. So up to degree 3 is there. Are we good? Now, the rest of the process is easy. I am now going to create up a simple linear regression model. Let's create up a model. I am going to name that as polymodel. Is equal to, why I am putting that as polymodel. Earlier I had the model by the name linreg. I am now going to change that to polymodel, but from the same class, linear regression. I'm still applying the linear regression, but this time I'm not going to train it on single variable x, but rather I'm going to train it on multiple number of variables which I've transformed from single variable. So I'll ask polymodel to get fitted dot fit on x underscore train underscore poly with respect to my y underscore train. Good. My model gets fitted on this data. Is that okay, team, till now? Give that a read. Transforming the training data fit underscore transform used to non-extend to generate new feature set that includes the polynomial features and interactions. Then I've got a transform test data and train the model. I have done this part so far, 14. Now I don't have to do many changes over there. I'm going to go back up here. This was my regression model done. I have done the training. I'm not going to look at the results. I'm going to ask to do the predictions. Okay, copying the back from the other part. Okay, go back up. Then I visualize the results for train data. I have not yet talked about the performance matrix, but I'm okay with the pace. No problems with that either. And then I looked at the results on the testing set data. This is what I've done. Good. The only thing that I'm going to change up here in this alt process is the model. The model here is a poly model which I trained on X train poly and Y train. Correct? So my predictions I will take up on with respect to here poly model, and here too I'm asking the poly model to do the predictions. Good. But here I'm going to use not the X train original but the polynomial, because my model is trained on the polynomial terms, so I need to provide it the polynomial terms only. Good. And let's put up these results as poly, P-O-L-Y, and here P-O-L-Y. So this is here, I will make the difference, same figure. Instead of predictions with the normal terms, I'll make it P-O-L-Y, and I'll change the name to polynomial regression. Good. And so does for the test data. I can change the predictions to X test poly, and I'll put the, it's not a linear regression model but a polynomial regression model. Let me execute all of this, then I'll ask this question. Now that may not look very good, isn't it? Why? Because that looks like a very broad line, and this is because it is happening because just only for one reason, that I'm using a plot function over there. If I use a scatter function, that may not look like the same way. Instead of plot, let me put up a scatter plot. Because the order of the equation is different, right? I might have a value once or a later. First of all, the first question, is it linear? Is that look linear? A straight line? It's not linear. It's a curved relation. I guess so not. Let's try out. Now, I don't have to do too many things. I can try out with a higher degree. It's a degree 3, my bad. Let's try out with degree 7. Okay. Let's see how does it look like. Now, look at this. Does it look like better a curved kind of situation on this line? This is on the train data, and this is here, it's on the test data. Better than degree 3, right? How will you judge it is better than degree 3? Basse. How will you judge it? You cannot just look at the visualization part. You cannot rely on the visualization directly, right? What you need to look at is the mean squared error and R2 values. How do I evaluate the performance? It takes care more of underfitting. I still can't say it. I can talk about it if I just try to go ahead and look at the performance matrix. I'll copy these two terms. Paste it up back. Let's put up MSC underscore train underscore with polynomial features. Good. And test underscore polynomial features. And I'll put up train. I have used the word poly. So you might have studied about the nomenclature part, right? People say that you need to name your variables very precisely. You can understand the usage of it now. That I have to just modify a single word and I am able to get the results in a different manner just by changing a single word, right? And later on I can plot up the results which I have used here. So I'll copy these results, not the results, but the prints of those. And what I'm going to bring onto the table is the results that I have got without polynomial features. So I'll copy this part. These are my results without the polynomial. This was a straight line relation, right? On straight line relationship, I got these results. Good. Now MSc train poly, and I'm putting a poly 5, a poly 7, right? We are using a 7-degree polynomial, right? That's what I've used so far. So MSc underscore train underscore poly, that's the variable. Test underscore poly, that's the variable. I missed out on underscore. This is here as well, underscore poly, and here too poly. Good. Now I can do it. So these are my results on training the polynomial equation with 7th degree polynomial. Good. You can compare now. My training error, which was 10, right? When I use the straight line, has now reduced on the training error to 9.8. But my testing error, which was 14, which was 11, has increased. So I'm able to reduce my training error, but eventually I've lost on my testing error. So is it good? Right? Earlier, my model was 63% accurate on training and 55% accurate on testing. Right? That was earlier situation. That was approximately a gap of 9%. Right? Approximately. Now what do I have is a gap of approximately 22%. If I change the relationship from a straight line to a curved line with a 7th degree polynomial, what I'm getting is an overfitted model. This is an overfit, right? This is slight overfit, or maybe an underfit. Good. Can I give that a try with maybe a lesser degree polynomial? Let's see. Let's give that a try with a degree of polynomial as 5. Good. So I've changed my degree 5. I can change my variable names later. Good. That looks kind of good to me. At degree 5. Maybe I have a better version at degree 6 or maybe at degree 4. But just for your convenience, a simple version. This is a comparative result between straight line and my polynomial line, same data. Good. Look at this. My training accuracy or training error reduced. Good. My testing error slightly reduced. Error on training data is less than testing data. Both situations. Acceptable. Ideal behavior. My error on training or my percentage of accuracy on training increased slightly. Slight increment. I had 63.3 with a straight line. Now I've got 64.9, close to 65. Slight increment over there. Without, right, approximately 2% increment over there. But I have not lost out on testing data. I have 55.5 earlier, now 55.3. Not so much significant dip on testing. So what I can assume is that a line or instead of a straight line, if I try to establish a relationship between y and x in this particular data as a curved line of degree 5, I have better results than a straight line. I'm not saying this is the perfect one. I'm yet not saying that. Maybe at degree 4, I have better results. Maybe at degree 8, I might have a better result. Make sense? So I need to fiddle around that at what degree I'll get the best results. But what do you think? Now look at this graph at degree 5. Just keep looking at this graph. You can make some assumptions with this graph. I'll change my degree now again. Yeah. Let's try. What degree do you want to try? Any number? Degree 4? Okay. Let's have a look at degree 4. At degree 4, it is going to create up to 4 degree polynomial features. That's how it looks like at degree 4. Almost flat line, Bessie. Isn't it? I guess it's more complicated relationship than this. Maybe let's look at degree 9. I guess at degree 9, we have the best possible result. That's the relationship that I've got. What I will not look at is the graph, but the results. Okay. Very bad, isn't it? On test data, I'm getting an R2 of 24.6. So degree 9 is not good at all. So I need to fiddle around at degree 4, 5, 6, somewhere close to that. Maybe at 6. At 5, I've seen the results. At 7, we have seen the results. Let's have a look at 6. So this is a manual thing, team. We would have to do that manually. That's where you require a human and AI while generating the model. That looks kind of good to me. Degree 6. That looks far more fit. 9.7, not very good. So at degree 5, I'm coming to a point that degree 5 looks the best possible solution to me. Make sense? So if I am now going to create up a model for this, I have two choices. Till now, I'm not saying these are my final choices. Till now, I have two choices. One choice that I can establish a relationship as a straight line using linear regression model, or I can establish a polynomial relationship with a degree 5, because degree 5 is the closest one that I can find out as of now, right? There can be multiple things that I can do. I can play around with the feature engineering. I can play around with the features terms. This may not be very much optimized set of features. I might have to standardize the set of features. I might have to scale them correctly up. That might give me some more different results. That's quite possible. Make sense? But as of now, what I can observe is that the results at degree 5 right? And my results you have all the things in the world to compare. Team, is it possible for you guys to compare both the results? Can you make some recommendation out of these two things? That which one is better, a degree 5 polynomial equation or a straight line equation? For this particular data set, predicting up a regression problem for this part. I'm not saying that this is your final solution. What I'm trying to say is that we have discussed about two solutions, two possible solutions to one problem. One is a linear regression with a straight line. Other one is a linear regression with the polynomial terms, or we call it as polynomial regression, right? Two solutions, one problem. I want to predict the sales values. So far, what I believe is a degree 5 polynomial equation is better representation as compared to a straight line. I hope so. You guys got the essence. You want to agree, still not able to agree. If there is a doubt, there's a question, ask it, Basi. Or there is a disconnect. I can still go in deep. I can extend this session maybe for next 1 hour. But team, don't keep it up to yourself. Why we should overlook the R2 values over the MSE? We should not overlook that, Basi, as of now. I should not be overlooking at those terms. Should not be at all. Because what I will say for you right now is this amount of dip that I see in the R squared value for the test data. So from 55.5, so originally 55.3 that I have on the straight line, I have now got a 55.5. So slight improvement on unseen data. There is an improvement in seen data too. Overall, if I look at that, I see an improvement in all the factors, the MSC for test, MSC for train, MSC R2 for train and R2 for test. So I see a straightforward improvement in all terms. But whenever you are trying to go in and evaluate a regression model, irrespective linear regression, multiple linear regression model, or any type of regression model, I am not going to overlook R2 over MSE. Never. I am going to look them in conjunction. Both R2 and MSE needs to be looked parallelly each other. They carry a different kind of information, yet they are both important. I will not only rely on MSE, I will not only rely on R2. Since I have not explained you R2 yet, so I will not comment on R2 too much. But what I can show you right now is the amount of difference that we have been able to generate from linear equation to polynomial, right? That's what I want you to observe. And I can definitely see that there is a difference. I have an improvement in all factors in polynomial terms as compared to straight line. If I take a degree 5, sensible? Basse. I do not know if I'm pronouncing it right, the name. Is there a way to calculate the overall average values of all in each of MSC and R2 for linear versus poly? Essentially, what you want to say, if I understood you correctly, that I want to try out polynomial equation with degree 1, 2, 3 and multiple number of terms and find out the average values across all those terms. Is that what you want to say? For MSC or an R2? No. Okay. So I interpreted it wrong. Is there a way to calculate the overall average values of all in each of MSC and R2 for linear versus poly? Does that mean linear versus poly degree 1, linear versus poly degree 2? And now, if you're thinking of that, okay, I have got a value divided by 4, divided by 3, no, that's not possible.
And with that, we have come to the end of this course. If you have any doubts or questions, ask them in the comment section below. Thank you and keep learning with Simplilearn.